Imagine a world so distant that one orbit around the Sun takes longer than all of recorded human history. A world we have never seen, but whose gravity we can feel bending the paths of icy wanderers beyond Neptune. This is not science fiction. This is not some wild theory cooked up by a fringe blogger in their basement. This is real. This is the most compelling, frustrating and dramatic hunt in modern astronomy, and it has been going on for nearly 200 years. Something massive is hiding in the darkness at the very edge of our solar system. Astronomers have been chasing its ghost for almost 2 centuries, and now, finally, we might be getting close. Let me take you back to the very beginning. Before you think this is just another internet conspiracy about Nibiru, or a rogue planet about to wipe us out, let me stop you right there. This is about hard, cold, measurable evidence, about orbits that shouldn't be there, about a mathematical ghost that keeps showing up in our data, no matter how many times we try to look the other way. For decades, astronomers have been peering out into the blackness beyond Pluto, and what they've found is a pattern that screams for a big explanation. There is a riddle out there, written in the movements of tiny frozen worlds, and it all started with a man who noticed something strange way back in the 1800s. You see, we have this history of finding planets by feeling their gravity before we ever see them. It happened with Neptune. Back in the 1840s, astronomers noticed that Uranus wasn't following the path it should have been. Something was pulling on it, something massive and unseen. So they did the math. They pointed their telescopes where the math told them to look, and boom, there it was, Neptune. A whole new planet discovered not by sight, but by the sheer force of its hidden presence. It was a triumph of human reason, and it set a dangerous precedent. If we could find one planet this way, why not another? Why not 2? Why not a whole family of dark lurking giants? That hunger led to a lot of false alarms. In the early 20th century, a wealthy astronomer named Percival Lowell became obsessed with finding a planet beyond Neptune. He called it Planet X. He spent years searching, building an entire observatory just for the hunt. He never found it. But after his death in 1930, a young farm boy named Clyde Tombaugh finally spotted a faint, slow-moving speck in Lowell's images. They called it Pluto, and for a while everyone thought the case was closed. Planet X was found. Mystery solved. But it wasn't. Pluto was tiny. Far too small to explain the gravitational oddities that Lowell had been chasing. It was a pebble, not a giant, so the anomaly remained. Astronomers kept looking. They found more and more objects in that cold, dark region beyond Neptune, a region we now call the Kuiper Belt. And as the discoveries piled up, a new pattern began to emerge. It wasn't an obvious thing at first. It was subtle, almost invisible. But by the early 2000s, a few sharp-eyed researchers started noticing something deeply strange. The most distant objects in the solar system, the ones that take hundreds or even thousands of years to circle the Sun, they weren't moving randomly. Their orbits were clustered. They were all tilted in the same direction, and they were all pointing toward the same part of the sky. Statistically, that should not happen. The odds of that kind of alignment occurring by chance were astronomically small. It was like finding a dozen marbles all rolled to the exact same corner of a room without anyone pushing them. There had to be a reason. There had to be a shepherd. And that is where we get to the heart of the mystery, the hypothesis that has split the scientific community for over a decade. A hypothetical planet, 5 to 10 times the mass of Earth, hiding out there 400 to 800 times farther from the Sun than we are. That is not a typo. 400 to 800 times. For context, Pluto is about 40 times farther from the Sun than Earth, so this thing would be 10 to 20 times farther out than Pluto. A frozen dark world, moving so slowly that it has barely shifted in the sky since the first telescopes were pointed at the stars. Its gravity would be the invisible hand, herding those distant icy wanderers into their strange alignments. We cannot see it. We have no direct image of it, but the math, the orbital mechanics, the sheer pull of its existence, that is getting harder and harder to ignore. Now, let me be honest with you. Not everyone is convinced. There is a very real and very vocal camp of astronomers who think this whole thing is a statistical illusion. They argue that our observations are biased, that we are simply finding the objects we can see, and we are seeing them in a pattern that exists only because of where we happen to be looking. They say that if you look at the data long enough, you will find a pattern in anything. It is the human brain doing what it does best, seeing order in chaos. And they might be right. That is the uncomfortable truth of science. It is not a collection of certainties. It is a series of best guesses that we constantly test against reality. But here is the thing. The evidence is getting stronger, not weaker. Every new distant object we find seems to fit the same pattern. Computer simulations show that a planet with the right mass and orbit could perfectly explain the clustering we see. And the search has never been more intense. The most powerful telescopes on Earth have been pointed into the darkness. Massive surveys are scanning the sky, pixel by pixel, looking for that faint moving dot. The discovery could come at any time. It might have already been captured in old data, just waiting for someone to notice it. If it is real, this would be the 9th planet of our solar system, a true giant hiding in plain sight. It would rewrite everything we thought we knew about the architecture of our cosmic neighbourhood. It would be the crown jewel of planetary discovery. But if it is not real, if this whole thing turns out to be nothing more than a trick of the light and the numbers, then the astronomical community has to confront a profound and humbling illusion. They must admit that they spent years chasing a ghost, a statistical phantom conjured by our own limited perspective. Either way, the stakes are enormous. How did we get here? And why, after 2 centuries of searching, are we only now close to an answer? That is the story we are about to tell. The hunt for a world we have never seen. A world that might not even exist, but a world that could change everything. Buckle up. This is going to get deep. The core of this mystery lies in understanding just how vast and dark that outer region really is. The Kuiper Belt, where we find Pluto and thousands of other icy bodies, is like the solar system's suburban sprawl. It extends from about 30 to 50 astronomical units, an astronomical unit being the distance from Earth to the Sun. That's a big area, but it's nothing compared to what lies beyond. Past 50 astronomical units, you enter the scattered disk, and past that you enter the realm of the true deep freeze, the Oort cloud, a theoretical shell of comets extending perhaps a light year from the Sun. In between, in that gap between 50 astronucleate and several hundred astronucleate, is where Planet 9 is supposed to live. This is a region so dark, so cold, that sunlight is a dim, distant memory. The Sun itself would appear no brighter than a very bright star, barely enough to cast shadows. Finding a planet there, a planet that does not generate its own light, and reflects only a tiny fraction of that faint solar glow, is the observational equivalent of finding a black marble on a coal field at midnight. The champions of this hypothesis, primarily Konstantin Batygin and Michael Brown from the California Institute of Technology, have spent years refining their model. Michael Brown is no stranger to planet-hunting drama. He is the man who killed Pluto. He discovered Eris, an object even more massive than Pluto, which forced the International Astronomical Union to finally define what a planet actually is, demoting Pluto in the process. Irony has a cruel sense of humour. The man who took away our 9th planet is now the leading voice trying to give us a new 9th planet. Back in 2016, Batygin and Brown published a paper that sent shockwaves through the astronomy community. They presented a detailed statistical analysis of the most distant Kuiper Belt objects, showing that their odds of being aligned by chance were less than 0.007%. That is a 1 in 14,000 chance. They calculated the gravitational fingerprint of the hypothetical planet, predicting its approximate orbit, its mass and its location. Since that landmark 2016 paper, the search has not stopped. Every major telescope has been enlisted. The Subaru telescope in Hawaii, with its massive light-gathering mirror and ultra-wide field camera, has been a primary workhorse, scanning huge swaths of the predicted orbital path. The Dark Energy camera in Chile, designed to map the accelerating expansion of the universe, has been repurposed to look for that slow-moving dot. Citizen science projects have even been launched, allowing thousands of home computers to sift through mountains of data, looking for the telltale sign of something that has shifted between two images taken on different nights. And the search has yielded tantalizing, if not conclusive, results. In 2018, a team of astronomers announced the discovery of a tiny world called 2015 TG387, nicknamed the Goblin. Its orbit was precisely aligned with the cluster of other distant objects, adding another bead to the string of evidence. More recently, another object, 2017 FO152, has been found, its path also matching the predicted pattern. With each new discovery, the probability of the cluster being a random fluke gets smaller. The statistical noose is tightening around a mathematical ghost. But the hunt is not just about the clustering. There are other peculiarities. For example, the planets of the inner solar system, from Mercury to Neptune, all orbit in a relatively flat disk, all in roughly the same direction. But the most distant objects, the ones we suspect are being herded by Planet 9, have highly tilted orbits. Some of them practically loop over the solar system like a halo. A massive, distant planet with an inclined orbit could have stirred up these objects over billions of years, tilting them out of the original flat disk. It would have acted like a cosmic egg beater, slowly churning the outer solar system into the strange configuration we see today. Furthermore, there is the problem of the cluster's origin. Why are these objects way out there in the first place? Normally, Kuiper Belt objects can be nudged outwards by Neptune's gravity, but only to a certain distance. Beyond that, they should be flung out of the solar system entirely, eventually becoming rogue planets drifting in interstellar space. Yet, these objects remain bound to the Sun on incredibly elongated, stable orbits. The only way to keep them locked into such far-flung orbits is to have a massive body, a shepherd, that is constantly interacting with them, preventing them from escaping. Planet 9 fits that role perfectly. It would be the gatekeeper of the outer solar system, the gravitational bulwark that holds the back door closed. Now, let us address the elephant in the room, or rather, the planet we have not seen. If Planet 9 is so massive, 5 to 10 Earth masses, why can't we just see it? The answer is distance and darkness. Its predicted orbit is so vast that it takes between 10,000 and 20,000 years to circle the Sun once. It is incredibly dim because it is so far away. A planet like Neptune, if placed at that distance, would be about 1 billion times fainter than the faintest star you can see with your naked eye. Imagine trying to find a single dim light bulb in a stadium that has been covered with a thick blanket of fog, and you are only allowed to look through a drinking straw. That is the challenge. It is not impossible, just monumentally difficult. It requires large telescopes, sensitive cameras, and a meticulously planned search strategy. There is also the possibility that Planet 9 is not a traditional rocky or icy planet, but something even stranger. Some theoretical models suggest it could be a primordial black hole, a tiny remnant of the Big Bang, the size of a grapefruit but with the mass of several Earths. This is a more speculative, but not entirely dismissed, possibility. A black hole of that size would be completely invisible to our telescopes, but its gravitational influence would be identical to a planet. The way we would find it is not by seeing it, but by looking for the faint, telltale flares of light that occur when interstellar gas and dust get sucked into its event horizon and heat up before disappearing forever. The hunt for Planet 9, in this case, becomes a hunt for tiny flickering flashes in the deep blackness. The implications of a successful discovery are staggering. It would not just be a new planet. It would be a window into the formation of the solar system itself. Our best models suggest the early solar system was a chaotic place, with giant planets migrating, jostling, and flinging smaller bodies everywhere. Planet 9 might be a core remnant of that era, a planet that was ejected from the inner system by a gravitational slingshot from Jupiter or Saturn, only to settle in a distant, stable orbit. It could hold clues to the original composition of the primordial disk, frozen in time for billions of years. It could also explain the tilt of the Sun's own axis, which is slightly off by about 6 degrees relative to the orbits of the planets. A massive, distant planet could have a subtle torque on the entire solar system, pulling the Sun's rotation axis out of alignment. Conversely, if Planet 9 is never found, if the data continues to be explained away by observational bias, the scientific community will have to go back to the drawing board. It would mean our understanding of the outer solar system's dynamics is fundamentally flawed. It would mean that some unknown process is creating this bizarre orbital alignment, a process we cannot yet conceive. It would be a humbling reminder that the universe is still full of surprises, and that our models, no matter how elegant, are just approximations of a reality far stranger than we imagine. The search continues. Every night, telescopes are pointed at the dark, scanning, waiting. The data piles up, the simulations run. The papers are written and rebutted. It is a detective story on a cosmic scale, a silent battle between human ingenuity and the vast, indifferent darkness. And that is the beauty of it. The mystery itself is the engine of discovery. Whether we find Planet 9 or not, the search has already forced us to look closer, think deeper, and map the edges of our knowledge more precisely than ever before. The ghost at the edge of the solar system is more than a planet. It is a question, and the answer, whatever it is, will be extraordinary. The story of Planet 9 is not new. In fact, it begins nearly 250 years ago, in the cold, quiet days of March 1781. That was when a British astronomer named William Herschel, scanning the heavens with a homemade telescope, stumbled upon something peculiar. He thought it was a comet at first, but it didn't look like any comet he had ever seen. It was a small, fuzzy disk drifting slowly against the backdrop of stars. Within months, other astronomers realized what Herschel had actually found. It was a planet, a new planet, the first one discovered since antiquity. They called it Uranus. Now, you might think that finding a whole new world would be the end of the story. But really, it was just the beginning, because almost immediately Uranus started acting up. It refused to follow the rules. Astronomers across Europe and America watched it year after year, and they began to notice something deeply troubling. Uranus was not where it was supposed to be. It was drifting off course, a little bit east, then a little bit west. The planet's motion was full of what they called perturbations, one tiny wobbles in its orbit that could only mean one thing. Something was pulling on it, something unseen. This is where a man named Alexis Bouvard enters the story. He was a French mathematician, a brilliant mind who dedicated himself to the science of celestial mechanics. In 1821, Bouvard published a set of tables predicting Uranus's orbit far into the future. These tables were based on the known laws of gravity and the positions of every other planet at the time. But as soon as he finished, Bouvard knew he had a problem. The tables didn't work. The observed positions of Uranus kept deviating from his predictions, and the errors were systematic. They were not random mistakes. They were persistent, stubborn, and growing. Bouvard was honest about it. He wrote in his notes that these discrepancies might be caused by some unknown force acting on the planet. But he had no idea what that force could be. He simply could not explain it with the gravity of any known object. So he published his flawed tables anyway, hoping that one day someone would solve the mystery, and solve it they did. But here's the thing that made it possible. The very technique that scientists use today to hunt for Planet 9. The idea of watching for orbital wobbles to detect an invisible world, that method had already proven itself once before. It was a technique forged in frustration and refined by genius. And it led to one of the greatest triumphs in the history of astronomy. The year was 1846. Two mathematicians working completely independently on opposite sides of the English Channel had taken up Bouvard's challenge. One was John Couch Adams, a shy and meticulous young man from England. The other was Urbain Le Verrier, a fiery and confident Frenchman. Both of them believed that the wobbles in Uranus's orbit were real, and both of them were convinced that a single hidden planet was the cause. They sat down with pen and paper, with nothing but Newton's laws and a mountain of observations, and they did something extraordinary. They calculated exactly where that unknown planet had to be. They pinpointed its mass, its distance, and its position in the sky. It was a mathematical shot in the dark, a gamble that could have easily failed. But it didn't. On September 23, 1846, Johann Galle, an astronomer at the Berlin Observatory, pointed his telescope to the exact spot Leverrier had predicted. And there it was. A faint blue-green disk, a new world. They called it Neptune. The discovery was a masterpiece of human reasoning. It proved that gravity could be used as a kind of cosmic radar, that the pull of an unseen object could be measured, and its location found, long before anyone ever laid eyes on it. It was one of the greatest moments in science, and it seemed for a brief and glorious moment that the solar system was finally understood. But science is never that tidy. Because even after Neptune was discovered and its orbit was measured, Uranus still had a tiny nagging problem. The anomaly did not fully disappear. A tiny residual wobble remained, a ghost of a perturbation that no one could explain. Some astronomers blamed it on Neptune's mass being slightly off. Perhaps their calculations of Neptune's gravity were just a little bit imprecise. But others whispered a more tantalizing possibility. What if there was another planet? A ninth planet even more distant lurking in the darkness beyond Neptune's orbit? The idea took root. It became a kind of obsession. And no one was more obsessed than Percival Lowell. Lowell was a wealthy Bostonian, a man of immense privilege and immense ambition. He was not a professional astronomer by training, but he had the money to become one, and he had a vision. He believed with all his heart that there was a hidden planet out there, a world he called Planet X. He was so convinced that he founded an entire observatory just to find it. Lowell Observatory, perched on a hill in Flagstaff, Arizona, was built for the sole purpose of hunting for this ghost. Lowell poured his fortune into it. He bought the best telescopes. He hired the best assistants, and for years he conducted a systematic photographic survey of the sky. Night after night, year after year, Lowell took photographs of the same regions of the zodiac, hoping to spot a faint moving point of light that would reveal his elusive Planet X. He scrutinized thousands of plates. He marked tiny dots that might be moving. He calculated and recalculated, but nothing ever came of it. The planet refused to show itself. In 1916, Percival Lowell died, a frustrated man. He had spent the last years of his life chasing a phantom, and he had failed. His reputation was tied to a planet he could not find, and many of his colleagues dismissed him as a crank. For over a decade, the search for Planet X went cold. Then, in 1929, a young man arrived at Lowell Observatory. His name was Clyde Tombaugh, and he was about as unlikely an astronomer as you could imagine. He was a farm boy from Kansas, a self-taught stargazer who had built his own telescopes out of farm equipment. He had sent his hand-drawn sketches of Jupiter and Mars to the observatory, and they had been so good that the director hired him on the spot. Tombaugh was given a monumental task. He was to continue Lowell's search, and he did it the old-fashioned way, through sheer grit and patience. His method was brutally simple. He would take 2 photographs of the same patch of sky several nights apart. Then he would load them into a machine called a blink comparator. This device would rapidly flash between the 2 images, back and forth, back and forth. Any star that had stayed perfectly still would appear fixed, but anything that had moved even a tiny amount would seem to jump, to blink in and out of existence. It was a mind-numbing job. Tombaugh would sit in a dark room for hours on end, staring at hundreds of thousands of faint specks of light, hunting for the one that moved. He did this for months. He compared millions of stars, and then, in February of 1930, he found it. A tiny dot, faint, moving slowly across the plate. Tombaugh knew immediately what he had. He had found a new planet. The world went wild. Newspapers trumpeted the discovery. It was named Pluto, after the Roman god of the underworld, a name suggested by an 11-year-old girl in England. And for decades, Pluto was celebrated as the 9th planet. It was hailed as Lowell's Planet X, the vindication of a man who had died searching. It was a beautiful story, but there was a problem. A big one. Pluto was tiny. From the very beginning, astronomers noticed that it was not the massive world they had expected. In fact, it looked like a tiny speck, barely a dot even in the most powerful telescopes. Over the following decades, measurements became more precise and the truth became unavoidable. Pluto's mass was minuscule. It was later estimated to be only about 0.2% of Earth's mass. That's roughly the same as our Moon. There was no way a world that small could have caused the gravitational wobbles attributed to Planet X. It simply did not have enough gravity. Pluto was not the answer, it was a coincidence. A small, icy world that happened to be in the right place at the right time. For years, astronomers tried to pretend otherwise. They kept looking. They kept hoping there was another planet further out, one that could explain the anomalies. But in the 1990s, something happened that changed everything. In 1989, NASA's Voyager 2 spacecraft flew past Neptune, and it gave us something we had never had before. A precise measurement of Neptune's mass. When scientists plugged that new number into their calculations, something magical happened. Uranus's orbital anomaly vanished. It disappeared completely. The entire reason for Planet X had been an error. The mass of Neptune had been slightly wrong, and once it was corrected, Uranus's orbit made perfect sense. There was no need for a hidden ninth planet. For a decade, the idea of Planet 9 was dead. Pluto was demoted to dwarf planet status in 2006. A controversial decision that broke the hearts of schoolchildren everywhere. And it seemed for a time that the solar system was finally complete. 8 planets. A neat, tidy little family. The ghost had been exorcised. But the solar system was not done hiding secrets. The old ghost of Planet X was about to return, in a form no one expected. The story took a sharp turn in the early 1990s, in a place far colder and more remote than anyone had imagined. Astronomers began to find other objects out there, beyond Neptune. Small icy worlds, dozens of them, then hundreds. A new region of the solar system was discovered, a vast frozen ring of debris left over from the birth of the planets. They called it the Kuiper Belt. And Pluto, it turned out, was not a lonely outlier. It was the first of its kind, a member of a large and populous family. The discovery of this belt was a revolution. It reshaped our understanding of the outer solar system, but it also told us something else. The Kuiper Belt had structure. It was not a random, chaotic snowball fight. There were patterns in the orbits of these distant, icy bodies, and those patterns were deeply strange. One of the most dedicated observers of this new frontier was a man named Michael Brown. He was an astronomer at Caltech, a young and ambitious researcher who became obsessed with the outer solar system. In the 2000s, Brown and his team began discovering large Kuiper Belt objects at a furious pace. They found Quaoar, an icy world half the size of Pluto. Then they found Sedna, a truly bizarre object in a highly elongated orbit that took it to incredible distances. And then, in 2005, they found Eris. Eris was a game changer. It was nearly the same size as Pluto, maybe even a little larger, and its discovery forced a fundamental question. Was Eris a planet? If so, how many more planets were out there? The answer ultimately was a new classification. Dwarf planets, and Pluto, the beloved ninth planet, was stripped of its title and reclassified alongside Eris as a dwarf planet. Michael Brown became widely known as the man who killed Pluto. But Brown was not done. He had helped shatter one mystery, but he had stumbled upon another, far more profound one. It happened as he and his team started cataloguing the orbits of the most distant objects they could find. They were looking for really extreme objects, the ones with orbits taking them far beyond the main part of the Kuiper Belt. These are the objects that spend most of their lives in a kind of cold storage, barely influenced by the gravity of the giant planets. They are the most pristine relics of the solar system's birth, and their orbits were supposed to be random, but they were not. In 2014, Brown and his colleague Chad Trujillo published a paper that raised eyebrows. They had been studying the orbits of the most distant known objects, like Sedna and a handful of others. And they noticed something that should have been a statistical impossibility. The orbits of these objects were not randomly oriented in three-dimensional space. Instead, they were all tilted in the same direction. Their elliptical paths, the long axes of their orbits, were all pointing in roughly the same way. It was as if someone had taken a group of commuters, all driving on separate roads, and found that every single one of them was pointing their car in the same direction. The probability of this happening by chance was astronomically low. Trujillo and Brown knew they had found something real. But what was causing it? The only explanation that made sense was a massive, unseen planet. A planet so far away that its gravity was reaching out across hundreds of astronomical units, herding these small icy worlds into alignment. Brown and Trujillo were cautious. They did not claim to have found a planet. They simply said the evidence was intriguing. But the idea was planted, and it grew. Over the next 2 years, Brown teamed up with another Caltech astronomer, Konstantin Batygin. Batygin was a theorist, a master of celestial mechanics and mathematical modelling. Brown was the observer, the one who knew the data inside and out. Together, they formed a perfect partnership. They locked themselves in an office and began the slow, painstaking work of trying to explain the observed clustering. They considered every possibility. Could the clustering be caused by an uneven survey of the sky? Maybe they had only looked in certain areas and missed objects that would break the pattern. But the data from other telescopes, including the wide field surveys that covered the entire sky, showed the same thing. Could it be caused by the combined gravity of all the Kuiper Belt objects? Brown and Batygin ran simulations, and the answer was a firm no. The Kuiper Belt itself was too diffuse, too lightweight, to produce such a strong alignment. Could it be a passing star, something that had swung by the solar system millions of years ago and stirred everything up? But the alignment was too tight, too precise. A passing star would leave a much more chaotic signature. One by one, they eliminated all the conventional explanations, and then they ran the simulation with a planet. They put a massive, distant world into their model, and they tuned its orbit, and it worked. A planet with a mass roughly 10 times that of Earth, orbiting at an average distance something like 20 times farther from the Sun than Neptune, on a highly elliptical and inclined orbit, could perfectly explain the clustering of the distant Kuiper Belt objects. The model was not just a good fit, it was stunningly precise. The planet's gravity created a kind of cosmic shepherd's crook, sweeping through the outer darkness and herding the small icy bodies into a specific alignment. On January 20, 2016, Brown and Batygin published their findings. The paper was titled, "Evidence for a Distant Giant Planet in the Solar System." It was not a discovery in the strictest sense. They had not seen anything through a telescope. They had not captured a single photon of light from this world. But they had done something very similar to what Adams and Leverrier had done for Neptune. They had detected a planet through its gravitational influence. They had used the same ancient technique, refined by the tools of the 21st century. The immediate reaction from the astronomical community was a mix of excitement and deep skepticism. Everyone remembered Percival Lowell. Everyone remembered the false alarm of Pluto. Could this be another mistake? Many astronomers pointed out that the data sample was still small. Only a handful of distant objects showed the clustering, and maybe the pattern would disappear as more objects were found. The skeptics had a point. The case for Planet 9 was compelling, but it was not yet proven. The only way to truly confirm its existence was to find it directly, to point a telescope at the right patch of sky and see a faint dot moving against the background stars. And that was the greatest challenge of all. If Planet 9 exists, and if it is as far away as Brown and Batygin suspect, it would be incredibly faint. It would be thousands of times fainter than the faintest star visible to the naked eye. It would be moving incredibly slowly, taking 20,000 years or more to complete a single orbit around the Sun. Finding it would be like looking for a single tiny cold ember in a vast dark field. You would need the world's most powerful telescopes. You would need to survey huge areas of sky, night after night, for years. And you would need to be lucky. The search for Planet 9 is currently one of the most active and exciting frontiers in astronomy. Teams of astronomers around the world are using telescopes like the Subaru telescope in Hawaii, the Dark Energy camera in Chile, and the massive twin Keck telescopes. They are methodically scanning the plane of the solar system where Brown and Battigin's model predicts the planet should be. It is a slow and methodical hunt. They are taking images of the sky, comparing them across multiple nights, and looking for anything that moves. It is a digital version of Clyde Tombaugh's blink comparator, but on a scale he could never have imagined. The search has been complicated by two major factors. First, the model predictions are not infinitely precise. Brown and Battagin can point to a region of the sky that is most likely for Planet 9, but that region is still enormous, covering thousands of times the area of the full moon. It is a huge haystack to search, and the needle is very small. Second, and more problematically, the most likely region for Planet 9 happens to lie in a part of the sky that is densely packed with stars from the Milky Way galaxy. It is the galactic plane, where the view is crowded with millions of bright and faint stars, making it extremely difficult to pick out a single world that is moving at a glacial pace. Despite the difficulty, the search continues, and it is not just professional astronomers who are involved. Citizen science projects have been launched, allowing amateur enthusiasts to help sift through the data. The world, it seems, is still captivated by the idea of a ninth planet. There is something deeply romantic about it, a return to the grand age of exploration where entire worlds were yet to be found. But what would it mean if Planet 9 is found? The implications would be profound. First, it would completely rewrite our understanding of the solar system's architecture. We currently think of our neck of the woods as a neat, orderly set of 8 planets in a disk. A planet like Planet 9 would be a rogue, a maverick on a tilted, elongated orbit. It would suggest that the early solar system was a much more violent and chaotic place than we imagined. It is thought that Planet 9 might be a failed core of a giant planet, one that started to grow at the dawn of the solar system, but was ejected from its original location by gravitational interactions with Jupiter or Saturn before it could fully form. It was then flung into the outer darkness, where it has spent billions of years, an almost dormant behemoth. Second, it would answer the question of what happened to the solar system's missing planets. Our current models of planet formation suggest that there should have been more than 8. Something snatched them away. Perhaps Planet 9 is the last of a lost generation, a survivor of the wreckage. Third, it would open up a new era of solar system exploration. If Planet 9 is found, you can be absolutely certain that we would send a probe to visit it. We have already sent spacecraft to Jupiter, Saturn, Uranus, and Neptune. The ultimate goal of many planetary scientists is to send a probe to orbit and land on a world no human has ever seen up close. Planet 9, if it is real, would be the ultimate target. It would be an entirely new class of world, a giant frozen sphere with its own system of moons and rings, a place that has been in perfect cold isolation since the beginning of time. And there is a deeper question, one that is rarely discussed in scientific papers. The same technique that we are using to find Planet 9 could also be used to find other things. If there is a planet out there, then the technique works. And if it works, then the same search patterns could reveal something else. Something we are not expecting. The history of astronomy is full of surprises. Every time we have built a bigger telescope or looked at the sky more carefully, we have found things we did not anticipate. Things that overturned our models. Things that made us realize how small our perspective truly is. The search for Planet 9 is not just a hunt for a single object. It is the systematic mapping of a region of space we have barely begun to explore. The Kuiper Belt and the region beyond it, the Oort cloud, are vast. They may contain thousands, even millions of worlds, and some of them may be larger than we think. Some may be waiting. In May of 2022, a study by a team of astronomers using data from the Transiting Exoplanet Survey Satellite, or TESS, added a new twist. They suggested that the orbital signatures of more than a dozen objects pointed to a planet with a mass between 4 and 8 times that of Earth, and an orbit not as tilted as initially thought. The exact parameters of the planet are being constantly refined, but the core evidence seems to be holding. The clustering of orbits is not going away. If anything, it is getting stronger. As new objects are discovered in the outer solar system, more and more of them are being found in the same aligned orbits. One of the most compelling pieces of evidence came from the discovery of a body designated 25D BP5Y9, nicknamed Kaju. This object had a wildly tilted orbit, tilted more than 50 degrees from the plane of the solar system. It was something of a statistical oddball. Its orbit was tilted so steeply that it could barely be explained by the known planets. But when Battigan and Brown ran their model of Planet 9, the orbit of Kaju fit perfectly. It was as if the planet was reaching out its gravitational hand and tilting this tiny world into a specific orientation. It was a piece of evidence that felt like a clue in a detective novel. As of today, in the middle of the 2020s, the hunt is still on. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to begin full operations in 2025. This is a game-changing instrument. It has an enormous mirror, a huge field of view, and a massive digital camera that will survey the entire visible sky every few nights. The Rubin Observatory is designed to find moving objects. It will find millions of asteroids, comets, and Kuiper Belt objects. And if Planet 9 is out there, the Rubin Observatory will almost certainly find it. It is the single best hope for a direct detection. It is the kind of instrument that could, in a single run, do what decades of manual searching could not. So the story of Planet 9 is not yet finished. It is a story that began with a planet that was in the wrong place, and a mystery that would not die. It is a story of eccentric millionaires and farm boy astronomers, of mathematical geniuses and patient observers, of hubris and triumph, of mistakes and revelations. It is a story about how we see the universe, and how the universe pushes back against our assumptions. And right now, at this very moment, somewhere out there, in the cold and absolute darkness, a planet may be moving. A world 10 times the mass of Earth, with a core of rock and ice, wrapped in a thick atmosphere of hydrogen and helium. A world that has not seen sunlight for billions of years. A world that is, by all accounts, the 9th planet of our solar system. It is waiting. It is a ghost that has walked the edges of our understanding for over a century. And someday, perhaps very soon, we will look through a telescope or scroll across a digital image, and we will find it. And when we do, the solar system will be made whole again. We will have our 9th planet back. The story we have followed so far, the hunt for a ghost planet, has been a tale of shadows and inference, of faint tugs on distant orbits and mathematical whispers. But to understand why such a search is even plausible, why astronomers are not simply chasing phantoms, we need to step back. We need to leave the familiar warmth of the inner solar system behind. We need to shift our perspective from the neat, orderly circles of the classical planets to a place that is cold, dark, and almost unimaginably vast. We need to talk about scale. Specifically, we need to talk about the frozen frontier. Most people, when they think of the solar system, picture a tidy little collection of planets. You have your inner rocky worlds, Mercury through Mars, and then your gas giants, Jupiter through Neptune, and that, they think, is that. The end. But they are missing the biggest part of the picture. Beyond Neptune's orbit, the solar system does not end. It just gets stranger. It opens up into a third zone, a sprawling ring of icy debris that we call the Kuiper Belt. This is not just a few lonely rocks floating in the dark. This is a massive, donut-shaped structure that starts roughly 30 astronomical units from the Sun, about 30 times the distance between Earth and the Sun, and it stretches out to about 50 astronomical units. To put that in perspective, if Earth were a marble sitting on a table, the Kuiper Belt would be a ring of dust stretching from here to the far wall of a huge gymnasium, and this belt is absolutely loaded. It is the solar system's attic, full of leftover junk from the formation of the planets over 4.5 billion years ago. You have dwarf planets like Pluto, which we used to call the 9th planet until we got smarter and realised it was just the biggest fish in a very, very big pond. You have Eris, Makemake, Haumea, and Quaoar. These are not tiny specks of dust. They are worlds in their own right, with their own moons, their own geology, their own frozen landscapes of methane and nitrogen ice. But they are just the celebrities. The real population of the Kuiper Belt is made up of hundreds of thousands, perhaps hundreds of millions, of smaller icy bodies. Comets, essentially. Frozen remnants of the primordial cloud that gave birth to everything we know. They orbit out there in the deep cold, silently, patiently. Now, here is the thing that really starts to twist your brain. The sun's gravitational influence, the invisible leash that keeps everything in the solar system tethered to it, does not just stop at the edge of the Kuiper Belt. Not even close. The sun's sphere of influence, the Hill sphere, extends far, far beyond that. We are talking about a distance of over 160 astronomical units, maybe even further. Beyond the Kuiper Belt, there is another structure, a ghostly spherical shell that surrounds the entire solar system, called the Oort cloud. This is the true edge of the solar system, a realm of trillions of comets, held loosely in the sun's weak gravity, waiting for a passing star to nudge them our way. But even the Kuiper Belt itself, the region right next door, is a land of shadows. We hardly know a thing about it. Think about this for a moment. As of the early 2020s, after decades of searching with the best telescopes on Earth and in space, we have catalogued only about 4,000 objects in the entire Kuiper Belt. 4,000. Out of what is estimated to be hundreds of millions. That is like standing on a beach, picking up a single grain of sand, and claiming you have mapped the whole shoreline. We are almost completely blind to what is out there. The vast majority of the Kuiper Belt, a region of space thousands of times larger than the space between Earth and the Sun, is completely unmapped. This is not a minor detail. This is the central mystery. Whenever you have a blind spot this large, there can be anything hiding in it. Anything. And it is in this deep, unmapped darkness that astronomers began to notice something very strange. They started cataloguing a special class of objects. Objects that did not behave like normal Kuiper Belt residents. They called them extreme trans-Neptunian objects, or ETNOs. These are icy bodies on orbits that are so elongated, so stretched out, that they take them far, far beyond the influence of Neptune. They are not just hanging out in the main belt. They are zooming out to hundreds of astronomical units from the Sun, on paths that are almost impossible to explain using the planets we know about. The first major clue that something was seriously wrong came in 2003. A team of astronomers led by Mike Brown, along with Chad Trujillo and David Rabinowitz, discovered an object that they would later name Sedna. And Sedna was a bombshell. Sedna's orbit was, and still is, one of the most bizarre in the entire solar system. It takes this little world, which is about 1,000 kilometers across, over 11,000 years to complete a single lap around the Sun. 11,000 years. The last time Sedna was where it is now in its orbit. The last ice age was just ending on Earth. Human civilization did not even exist. But that is not the weirdest part. The weirdest part is where its orbit takes it. At its closest approach to the Sun, Sedna gets to about 76 astronomical units. That is so far out that Neptune's gravity, the most influential force in the outer solar system, has absolutely zero effect on it. It is completely isolated, completely alone. According to our models of how the solar system formed, Sedna should not be there. It should have been flung away or pulled into a more circular orbit billions of years ago. Its existence was a glaring, screaming anomaly. For years, astronomers were baffled. They had one weird object, and one weird object could just be a fluke, a cosmic accident. You need a second data point to build a case. And that second data point did not come until 2014. That year, the same team discovered another object, officially called 2012 VP113, but more affectionately nicknamed Biden. And Biden had the same kind of orbit. It was isolated, extremely elliptical, and its closest approach to the Sun was also far beyond Neptune's reach. Two objects sharing the same impossible orbital signature. The pattern grew. As telescopes improved and surveys got deeper, astronomers started finding a handful of other extreme objects. Sedna, Biden, a few others. And they all shared a very specific, very bizarre trait. Their orbits were not just weird in shape, they were weird in orientation. They all seemed to be pointed in roughly the same direction in the sky. Their long axes, the lines that mark the furthest points of their orbits, were all tilted and aligned in a way that should not have happened by chance. It is like finding a handful of marbles scattered on a floor, but every single one of them is pointing directly at the same spot under the couch. It is not random, it is a clue, and so the astronomers did what they always do. They ran the numbers. They calculated the probability that this orbital alignment could have occurred naturally by random chance in a solar system governed only by the gravity of the 8 known planets. The odds they came up with were staggering. We are talking about odds of roughly 1 in 15,000. To put that in perspective, you have a better chance of being struck by lightning in your lifetime. You have a better chance of winning a small lottery prize. The chances of this alignment being a coincidence are astronomically, laughably low. Something was herding them. Something massive, with a powerful gravitational field, was reaching out across hundreds of astronomical units of empty space and steering these icy worlds into a common pattern. But what? What kind of force could reach that far? What kind of object could remain completely invisible to our most powerful telescopes, while affecting the orbits of bodies that are billions of kilometers away? The answer, to many astronomers, was obvious. It had to be a planet so distant that it never comes close enough to the Sun to reflect enough light for us to see it. A planet that is just sitting out there in the darkness of the Kuiper Belt, herding its flock. The ghost we were hunting at the beginning of this story had a name, and a location, and a growing mountain of evidence pointing directly at it. The question was no longer if it existed, it was how we were going to find it. To understand the full magnitude of this hunt, we must consider the nature of the quarry. This hypothetical planet, often called Planet 9, is not a small, rocky world like Earth. Based on the gravitational nudge it is exerting on the etnos, astronomers have deduced its mass, and the number they keep arriving at is roughly 5 to 10 times the mass of Earth. That is significant. That puts it in a category all its own. It is bigger than any terrestrial planet, but smaller than the ice giants Uranus and Neptune. It is a class of world we have never seen before in our own solar system, a super-Earth. But calling it an Earth is misleading. This is not a warm blue marble. If it exists, Planet 9 is a frozen hellscape. The surface temperature so far from the Sun would be somewhere around minus 250 degrees Celsius. That is barely above absolute zero. The atmosphere, if it even has one, would be frozen solid, a blanket of nitrogen and methane ice, coating a dark, rocky, and possibly exotic ice core. It is a world of eternal, crushing darkness, warmed only by its own residual heat from formation, which would be negligible. Its orbit, if it exists, is the key to its invisibility. A typical planet in the solar system, even a distant one, follows a relatively circular path. We see them because they are constantly sweeping through space, and at some point in their orbit, they come close enough to the Sun to reflect its light. We found Neptune in the 19th century because its orbit brought it into view. But Planet 9, if the models are correct, does not do that. Its orbit is not circular. It is a stretched out, highly elliptical oval. It takes this planet, by some estimates, between 10,000 and 20,000 years to complete a single orbit. To put that in human terms, the last time this planet was where it is right now in its distant path, our ancestors were still painting on cave walls. The entire span of recorded human history, from the invention of writing to the launch of the James Webb Space Telescope, represents only a tiny fraction of one single year for Planet 9. And most importantly, the point in its orbit where it is farthest from the Sun, its aphelion, is the part that is easiest to hide. The models that best explain the alignment of the etnos suggest that Planet 9 spends most of its time at the far end of its orbit, at a distance of something like 600 to 1200 astronomical units from the Sun. At that distance, the Sun is not a bright disk. It is just a very bright star, a pinprick of light in the darkness, providing almost no illumination whatsoever. A planet at that distance would receive about 1/4 millionth of the sunlight that Earth receives. It would be dimmer than the faintest stars we can see with the naked eye. telescopes sweeping the sky are not looking for a dark, cold rock moving slowly against a backdrop of billions of faint stars. They are looking for a needle in a cosmic haystack, and the needle is painted black. This is where the search becomes a story of patience, of statistical analysis, and of ingenious detective work. Two of the leading hunters, Konstantin Batygin and Mike Brown from Caltech, did not try to find it by blind sweeping. Instead, they used the orbits of the known ETNOs as a net. They ran massive computer simulations, feeding in the exact positions and velocities of Sedna, Biden, and the others. Then they asked the computer to simulate billions of possible configurations of a distant planet. They tweaked its mass, its orbit, its tilt. They ran time forwards and backwards, over billions of simulated years, to see which single solitary planet could consistently produce the exact orbital clustering we observe today. The result was a narrow set of possible locations. They did not find the planet itself, but they drew a map of where the planet is most likely hiding. It was a massive map, covering hundreds of square degrees of sky, but it was a start. And so the search continues, using the most powerful tools humanity has ever built. The Subaru telescope atop Mauna Kea in Hawaii, with its massive 8-meter mirror and its incredibly wide-field camera, is a primary weapon. It can sweep huge swaths of the sky in a single night, capturing images of millions of faint objects. The hunt involves taking images of the same patch of sky on different nights, sometimes weeks or months apart, and then sitting behind a computer, writing algorithms to detect the tiniest impossible motion. A planet that is 600 astronomical units away moves so slowly against the background stars that its shift is usually less than the width of a single pixel over several nights. You are literally trying to detect the slowest crawl in the universe. Then you have to confirm that the motion is not an artifact, not a cosmic ray hitting the detector, not a tiny flaw in the camera. You have to observe it again and again to be absolutely certain. There have been false alarms and dramatic moments. In 2019, a study of data from the Voyager spacecraft suggested that a planet might be perturbing the orbits of both ETNOs and the trajectories of the spacecraft themselves. The evidence was tantalizing but ultimately inconclusive. Meanwhile, the original discovery team has had to fend off skepticism from the wider astronomical community. Some researchers argue that the orbital clustering we see might be the result of a selection bias. They say that our telescopes are simply better at finding objects that are aligned in that particular way, and that we are missing all the ones that are not. It is a valid criticism, and it is one that Batygin and Brown have spent years trying to refute by running simulations that account for the exact survey capabilities of their telescopes. The bottom line is that the statistical anomaly has not gone away. It has only grown stronger. The search for Planet 9 is more than a quest for a single object. It is a fundamental test of our understanding of the solar system. If it is found, it will rewrite textbooks. It will change our definition of what a planet can be and where it can exist. It will explain the strange orbits of these icy sentinels, and it will tell us that our solar system is not a neat 9-planet affair, but a dynamic structure with planets scattered across a staggering range of distances. If it is not found, it will force us to think even more creatively. Perhaps the clustering is caused by a passing star that grazed the outer system millions of years ago. Perhaps it is caused by a primordial instability in the early solar system that we do not yet understand. Perhaps the ghost is something else entirely, a rogue planet captured from interstellar space. Every night, astronomers point their telescopes at a piece of the sky that contains the faintest glimmer of a possible answer. They are looking for a dot that moves. They are looking for the 9th planet. And so, the stage was set for what would become the most electrifying detective story in modern astronomy. For years, the whispers had been growing, a low hum of suspicion in the scientific community that something was out there, tugging at the orbits of the most distant known objects in our solar system. But whispers aren't proof, and in science, proof is everything. That all changed in January of 2016, when a single paper landed in the pages of the Astronomical Journal like a bomb going off. The title was calm, almost clinical, evidence for a distant giant planet in the solar system. But the contents were anything but calm. This was the shot heard round the astronomical world. Two researchers from the California Institute of Technology, Caltech, had done the math, run the simulations, and come to a conclusion that was either going to rewrite the textbooks or go down in history as one of the most spectacular wild goose chases of all time. The two men behind this bombshell were a study in contrasts. First, there was Konstantin Batygin. He was young, barely 30 years old when the paper dropped, a Russian-American planetary dynamicist with a thing for numbers that most people can't even wrap their heads around. Batygin's specialty was orbital mechanics, the physics of how things move in space, and he lived and breathed computer simulations. If you gave him a gravitational problem, he could build a virtual model of the solar system on a supercomputer and watch it play out over billions of years. The guy had a mind like a steel trap, and the kind of patience that comes from watching tiny little digital planets dance around on a screen for months on end. He was quiet, methodical, the kind of scientist who thinks 3 steps ahead while everyone else is still tying their shoes. But the real star power in the room belonged to his collaborator, Mike Brown. Now, if you know anything about planetary science, you know the name Mike Brown. He was already a legend, and not necessarily in a good way in every corner of the world. In 2005, Brown discovered Eris, an icy world out in the Kuiper Belt that was about the same size as Pluto. That one discovery set off a chain reaction that ended with the International Astronomical Union reclassifying Pluto as a dwarf planet. Mike Brown became known forever as the man who killed Pluto, and you better believe he got some hate mail for that. But Brown didn't care about the drama. He cared about finding things. He had a knack for staring at the sky, at the most far-flung objects, and realizing that the patterns didn't make sense. So when he came knocking on Batygin's door with a hunch that something big was herding these distant worlds like a cosmic sheepdog, Batygin listened. Their method was pure science, and it was beautiful. They focused on 6 objects, not 600, not 6,000, just 6. These were extreme trans-Neptunian objects, or etnos, which is a fancy way of saying they were rocks or icy bodies orbiting way out past Neptune, at distances hundreds of times farther from the Sun than Earth is. And all 6 of these objects had something weird in common. Their orbits, the long, stretched-out ellipses that trace their path around the Sun, were all pointing in the same general direction. They were all clustered in the same quadrant of space. And even weirder, they were all tilted, inclined at the same angle, as if they had all been shoved by the same invisible hand. Now, if there was no hidden planet out there, if the solar system was just the 8 planets we know, and a whole bunch of leftover debris, you'd expect these orbits to be random. Random is the natural state of things. A bunch of icy rocks wandering around in the dark don't coordinate their movements. They get kicked around by Neptune's gravity. They get nudged by passing stars. They scatter every which way. So the fact that these 6 orbits were all aligned like arrows pointing at a target you couldn't see, that was a red flag the size of a planet. Batygin and Brown did the statistical grunt work. They calculated the odds of this clustering happening by pure chance. And here is where the numbers get absolutely staggering. They came up with a probability of 0.007%. Let me put that in terms you can feel. That is roughly 1 in 14,000. You have a better chance of flipping a coin and getting heads 14 times in a row. You have a better chance of being struck by lightning in your lifetime. The odds were so astronomically small that the only reasonable explanation was that something out there was causing it. Something massive. Something that had been hiding from us for as long as humans have been looking up at the stars. Now, a suspicious clustering is one thing. But in science, you don't get to claim a planet just because the numbers look funny. You have to build a case. You have to prove that the thing you're proposing actually works. And that's where Konstantin Batygin's computer simulations came into play. He spent months, probably longer, running thousands and thousands of models. He would set up a virtual solar system with the Sun in the middle, all 8 known planets doing their thing, and then he would add a hypothetical planet. He would give it a mass, say 5 times that of Earth. He would give it an orbit, say 500 astronomical units from the Sun. Then he would let the simulation run for millions of years, watching how the gravity of this phantom world affected everything else. He ran simulations with different masses, different distances, different tilts. He ran versions where the planet was closer in, and versions where it was farther out. He ran versions where it was big and heavy, and versions where it was smaller and lighter. And slowly, after all that number crunching, a best fit solution started to emerge. It was like tuning a radio, adjusting the dials until the static cleared and you could hear the music. The picture that came into focus was this: a planet, a real honest-to-goodness planet, with a mass somewhere between 5 and 10 times that of Earth. That puts it in a class we call a super-Earth. It's bigger than a rocky world like ours, but not as big as the gas giants like Neptune or Saturn. It's a type of planet we see all over the galaxy in other solar systems, but it's conspicuously absent from our own backyard. This thing, if it existed, would be the most exotic planet in our entire solar system. And its orbit was a doozy. We're not talking about a nice neat circle like Earth's. No, this was a long, stretched-out ellipse, an oval that takes it on a wild ride. At its closest point to the Sun, it might swing in to around 200 astronomical units, but at its farthest, it could be out past 800 astronomical units. For reference, Pluto is at about 39 astronomical units. 800 astronomical units is more than 20 times farther away. The numbers become almost meaningless at that scale. But here is the kicker: the orbital period, the time it takes for this world to complete one full lap around the Sun. Batygin and Brown's best models put it at somewhere between 10,000 and 20,000 years. Think about that for a second. One full year on this planet, one journey around the Sun, takes longer than the entire span of recorded human civilization. The pyramids of Giza were built about 4,500 years ago. That's less than half a year on this world. The last ice age ended about 11,000 years ago. That's barely more than half an orbit. If you were standing on the surface of Planet 9, assuming it had a surface, and you were born at its perihelion, its closest approach to the Sun, you would die of old age long before it reached its aphelion, its farthest point. This world is so far out that the Sun, from its surface, would look like nothing more than a bright star. You could cover it with the head of a pin held at arm's length. It would not look like a day. It would look like a pale, unblinking point of light, alone in an ocean of blackness. Now, this hypothetical world isn't just a lonely wanderer. If it's real, it's been doing a lot more than we realize. Batygin and Brown's calculations showed that the same gravitational influence that herds those 6 weird objects could also explain the extreme tilts of other distant bodies. There are objects out there that orbit the Sun at wild angles, almost perpendicular to the plane of the solar system, like they were knocked sideways by some giant cosmic pool cue. Planet 9's gravity could be the reason for that. And here's a really wild one. Our own Sun has a slight tilt to its axis, a 6-degree wobble, relative to the plane of the solar system. Astronomers have never had a good explanation for that. But a massive planet lurking out on the edge, slowly tugging on everything, it could account for that little tilt. It's like a gravitational ghost that's been secretly shaping the entire architecture of the outer solar system for billions of years. The scientific community, needless to say, went into a frenzy. But the most telling reaction came from the top. Jim Green, who was then the director of planetary science at NASA, basically the head honcho for all things planets in the United States, went on record. He said the evidence was stronger than it had ever been before. Those are big words from the guy who oversees the missions that have wandered through our entire solar system. But even as the excitement built, Batygin himself stayed grounded. He knew the golden rule of planet hunting. He said it himself, and it's a line that should be carved into every observatory wall. Until it's caught on camera, it doesn't count as real. You can have all the math in the world. You can have simulations that match perfectly. You can have odds of 1 in 14,000. But the universe doesn't care about your math. The universe plays by its own rules. Until you point a telescope at the right patch of sky, and you see a faint moving dot of light, it's still just a hypothesis. It's still just a ghost. The media, of course, had a field day. Headlines around the world screamed that a real ninth planet had been found, which technically was not true. It hadn't been found, but the story was too good to pass up. The man who killed Pluto was now trying to bring back a bigger, badder planet to take its place. It was the kind of narrative that writes itself. Telescopes around the globe, and even some in space, began scanning the predicted patch of sky. They didn't know exactly where to look. The orbit was too uncertain for that. But they had a general region, a vast, dark swath of the heavens where Planet 9 might be hiding, reflecting a faint glimmer of ancient sunlight. It was a needle in a haystack, and the haystack was bigger than anything humanity had ever tried to search. A decade-long hunt had officially begun, but not everyone was convinced the clustering was really there. Some astronomers argued that the clustering was an illusion, a quirk of observational bias. You have to understand, when you look at the most distant objects in our solar system, you are not just seeing everything that's out there. You are only seeing the ones that are bright enough, or big enough, or in the right part of their orbit to be visible from Earth. It is like standing in a dark forest with a small flashlight. You are only going to see the trees that the beam hits. You might convince yourself that all the trees in the world are clustered in one direction, because that is the only direction you can see. This became the central counter-argument, the voice of healthy skepticism that keeps science honest. A group of astronomers, led by a researcher named Corey Shankman, published a paper using data from a survey called OSS-OSS, the Outer Solar System Origins Survey. They argued that when you account for the places astronomers had actually been able to look, the clustering Batygin and Brown had seen wasn't statistically significant. They claimed it was a selection effect, meaning we were only finding objects in that part of the sky, because that's where we were pointing our telescopes when the conditions were right. Batygin and Brown pushed back hard, and this is where the story gets really interesting, because it became a battle of modelers versus observers. Batygin refined his simulations. He incorporated the exact observational biases of every survey ever conducted. He built a virtual copy of the search strategy itself, complete with the blind spots and the limelight zones, where telescopes were most likely to find things. Then he ran the numbers again, and again the signal persisted. The clustering was too tight, too perfectly aligned to be a trick of the light. In fact, the more he accounted for the bias, the stronger the signal seemed to get. It was like listening to a faint radio transmission through static. The more you filter out the noise, the clearer the voice becomes. And that voice was saying, something is out there. But even as the statistical war raged, a different kind of evidence began to pile up. It came from the very edge of the observable solar system, from a class of objects that orbit the Sun in what we call the scattered disk. These are objects that have been violently thrown out of the main Kuiper Belt by Neptune's gravity, flung into long, unstable orbits, and some of them have orbital tilts that are just bonkers. They are tilted by 50, 60, even 90 degrees relative to the plane of the solar system. For a long time, astronomers couldn't explain why these objects were so tilted. It takes a lot of energy to tilt an orbit that much. Neptune can do some of it, but not all of it. Planet 9, however, could do it easily. In Batygin simulations, the massive planet's gravity acted like a cosmic whisk, stirring up the outer solar system and throwing objects into all sorts of extreme inclinations. The predicted pattern of those tilts matched the observed pattern perfectly. It was another piece of the puzzle, another fingerprint at the crime scene. Then came the most tantalizing clue of all, a signal that some astronomers believe might be a direct detection. In 2022, a team of researchers led by Mike Brown, the co-founder of Planet 9 himself, published a paper on an object designated 2050 BP51, which they nicknamed Kaju. This thing was a weirdo. It was a small, icy world about 400 astronomical units from the Sun, and it had an extreme orbit that was tilted a staggering 54 degrees relative to the solar system's plane. The orbit was so weird that it could only be explained by the gravitational influence of a massive planet far away. Without Planet 9, the standard models of solar system formation could not produce an orbit like this. It just wouldn't work. The chances of it forming naturally were virtually zero. It was like finding a single chess piece in the middle of an empty desert. You know someone put it there, but even with all this evidence, the search continued to be a slog. The reason is simple. Planet 9, if it exists, is incredibly faint. It is not a gas giant like Saturn or Jupiter. It is a super-Earth, an icy, rocky world that is probably cold and dark beyond anything we can imagine. Its atmosphere, if it has one, would be frozen onto its surface. It would not shine with the reflected glory of Jupiter. It would be a dim, charcoal-coloured dot, moving against a background of billions of other dim dots. Finding it is not like looking for a star. It's like looking for a specific grain of sand on a beach. You can narrow down the search area, but you still have to sift through a mountain of data. The actual search involves telescopes like the Subaru telescope in Hawaii, which has a massive 8.2-metre mirror. It can see incredibly faint objects, and it has a wide field of view, meaning it can scan large patches of sky relatively quickly. The strategy is simple in theory, brutal in practice. You point the telescope at a specific patch of sky, take a series of images over several nights, and then you compare them. If there is a planet out there, it will have moved slightly between exposures. It will be a tiny dot that shifts position relative to the fixed background of stars and galaxies. You then subtract the background, and you look for moving dots. This is where the human element comes in, or in modern times, the machine learning element. Astronomers have developed algorithms that can sift through millions of data points and flag potential moving objects. But the false positive rate is astronomical. Every faint asteroid in the main belt, every piece of space junk, every cosmic ray hitting the detector can mimic the signal of a planet. Each candidate has to be verified by human eyes, and most of the time it turns out to be nothing. There was a moment in late 2019 when the search nearly bore fruit. A team in France, using data from the Hyper-Suprime cam on the Subaru telescope, thought they had found something. It was a faint dot that moved in the right way, in the right part of the sky. The astronomers were ecstatic. They had been searching for years, and this looked like the real thing. They did their due diligence. They checked their data. They ran their calculations. They even brought in Batygin and Brown for a consultation. For a few weeks it felt like the discovery of the century was imminent. But then the follow-up observations came in. The telescope looked at the same patch of sky on a different night, and the dot was gone. It had not moved as expected. It had simply vanished. It was a false alarm, probably a faint star that had flared up, or a glitch in the detector. The disappointment was crushing. It was like standing on the edge of a canyon, hearing a voice below, and then realizing it was just the wind. But the search did not stop. It could not stop, because the stakes were too high. Let me explain why this matters beyond just the thrill of discovery. If Planet 9 is real, it changes everything we think we know about the formation of our solar system. The standard model, the Nice model, named after the city in France where it was developed, says that the giant planets were formed much closer to the Sun, and then migrated outward, scattering smaller bodies as they went. But that model has trouble explaining the existence of a super-Earth in the outer solar system. Super-Earths are common around other stars, but we have never found one in our own system. We have small rocky worlds and we have gas giants. That gap in the middle is a mystery. If Planet 9 exists, it means our solar system might not be the quiet, orderly place we thought it was. It means there might have been a time, in the early days of the solar system, when there were multiple super-Earths, and most of them were ejected into interstellar space. Only one, Planet 9, remained, flung to the outer edge by the gravity of Jupiter or Saturn. It would be a survivor, a lonely remnant of a more chaotic past. Furthermore, the existence of Planet 9 would have implications for the search for other planets. If a super-Earth can form and survive in the outer solar system, It means that our system is not as unique as we thought. It would increase the probability that other solar systems harbour hidden worlds at their edges, far from their suns. It would give a new impetus to the search for exoplanets at very wide orbits, a population that current surveys mostly miss. And it would tell us something fundamental about the dynamical evolution of planetary systems. It's not just about finding a rock in the dark. It's about understanding the full range of possible outcomes when a cloud of gas and dust collapses into a star and planets. And the search continues to this day. The Vera C, Rubin Observatory currently under construction in Chile, is expected to revolutionize the hunt. It has a massive 8.4-meter mirror and an enormous 3-gigapixel camera. It will survey the entire southern sky every few nights, generating petabytes of data. It is designed precisely for this kind of work, finding moving objects in the darkness of the outer solar system. When it comes online, sometime in the mid-2020s, it should be able to either find Planet 9 or rule out its existence in a significant fraction of the search space. If Planet 9 is there, the Rubin Observatory will likely find it within the first year or two of operations. It is the cosmic net that may finally catch the ghost. But there is another possibility, a darker one. What if Planet 9 doesn't exist? What if the clustering and the tilts are all just a statistical fluke, a parlour trick played by the chaos of the outer solar system? That would be a setback, yes, but it would also be a profound discovery. It would tell us that our understanding of orbital dynamics is incomplete. It would force us to re-examine the models, to look for new physics, perhaps even for the gravitational effects of a primordial black hole or a dark matter clump. The absence of a detection after a thorough search would be just as important as the detection itself. Science is not about being right. It is about finding out what is true, regardless of what we want to believe. Batygin and Brown have kept the faith. They have continued to refine their predictions, narrowing down the probable orbit as more data trickles in from the far reaches of the system. In 2021, they published a paper that incorporated the orbits of 5 new extreme trans-Neptunian objects, bringing the total to 11. The clustering was still there. The signal was even stronger. They have also predicted the existence of a second, even more distant planet, a hypothetical Planet 10, to explain some of the more extreme outliers. But that is a story for another day. So where does that leave us as of this moment? We are in a strange place. We have a hypothesis so strong that many scientists would bet their careers on it. We have a prediction that has not been disproven despite years of searching. We have a named candidate, a mass, a distance, a period. And yet we have no photograph. We have no smoking gun. We are like a jury with all the circumstantial evidence we could want, but no body. And the defendant, Planet 9, remains silent in the darkness, a ghost of the outer dark waiting to be discovered. The search for Planet 9 is not just a scientific endeavour, it is a human one. It is a story of patience, of obsession, of the refusal to let the darkness win. It is the story of 2 men who dared to look at a handful of tiny frozen rocks and saw the shadow of a world. It is the story of a civilization that looks up at the night sky and wonders what else is out there. And it is the story of the long, slow march of discovery. One by one, over decades, we are pushing back the frontiers of the unknown. We have sent spacecraft to every planet from Mercury to Neptune. We have walked on the moon and we have landed on an asteroid and a comet. But there is a part of our own backyard that remains completely unexplored, a realm where the sun is just a star and the planets are just whispers in the dark. That is where Planet 9 waits, and one day we will find it, or we will prove it doesn't exist. Either way, the answer is out there, and the hunt continues. But let's think about what all this means. Let's get real about the implications. Because if Planet 9 actually exists, it doesn't just add a new dot to our map. It changes the entire picture. It shatters the way we think about our solar system, about how it formed, about what's even possible in this cosmic neighbourhood we call home. And that's a big deal. For decades, we've walked into classrooms and looked at those diagrams, those neat little posters of the solar system with the sun on the left and the planets lined up like ducks in a row. Mercury, Venus, Earth, Mars, the asteroid belt, then the gas giants, Jupiter, Saturn, Uranus, Neptune, and then, way out at the edge, a sad little Pluto if we're feeling generous. It's clean, it's orderly, it makes sense. But the first implication of a real Planet 9 is this: that picture is wrong. Not just a little wrong, fundamentally wrong. Our solar system's architecture would be fundamentally different from what we teach any child. Instead of 8 planets with a clear, comforting inner and outer divide, we would have a distant giant sitting out there in a vast, nearly empty frontier. Think about the distances for a second. Neptune orbits the Sun at about 30 astronomical units. 1 AU is the distance from Earth to the Sun, roughly 93 million miles. So Neptune is about 2.8 billion miles away. That's far. That's the end of the line, or so we thought. But Planet 9, if it's real, sits at a mind-bending orbit that takes it anywhere from 200 to 1200 ASTRO-UQ from the Sun. That's not just farther away than Neptune. That's farther away than almost anything we've ever found orbiting our own star. It would be in a realm where the Sun is just a bright point of light, not a warm, life-giving disk. It would be a dark, cold, lonely giant, and its existence would mean that our solar system doesn't end at Neptune. It doesn't end at the Kuiper Belt. It extends out into this vast silent darkness where objects move on timescales measured in tens of thousands of years. And that thought alone rewrites everything we thought we knew. It would be like finding out your house has a massive hidden room you never knew existed. A room bigger than the entire house you've been living in your whole life. But the second implication is even more profound, and it digs into the bone of planetary science itself. It forces us to reshape our entire model of solar system formation. How do you get a planet like that? A super-Earth, a world maybe 5 to 10 times the mass of Earth, sitting way out in the cold? Did it form in place, like a seed that somehow grew in a region of space that should have had almost nothing to build with? That's hard to swallow. The early solar system was a chaotic place, a swirling disk of gas and dust, and planets are born from the leftovers of a star's birth. But out at those distances, the material would have been incredibly sparse. It's like trying to build a sandcastle out of a few grains scattered on a beach. It doesn't seem possible. So the alternative is that Planet 9 is an interloper. It might have formed much closer to the Sun, maybe in the region where the gas giants were born, and then some violent gravitational game of cosmic billiards threw it out into the deep freeze. Think about that. A young Jupiter or Saturn, still forming, still getting its act together, could have kicked this massive protoplanet out like a hockey puck. And just like that, it was gone. Banished to the outer darkness, where it's been drifting for 4.5 billion years. That scenario isn't just plausible. It's actually predicted by some of our best computer simulations of the early solar system. Those simulations often produce a planet that gets ejected entirely, lost to interstellar space, but sometimes they leave one behind, a straggler, a survivor, hanging on in a distant, eccentric orbit. And that survivor might be Planet 9. So its existence would be a fossil, a relic from the most turbulent era of our solar system's history, preserved in ice and darkness. And then there's the third implication, which is a little less mind-bending but maybe more practical. It's the idea that Planet 9 could actually be the protector of the inner solar system. It sounds like science fiction, but hear me out. Way out beyond Neptune, past the Kuiper Belt, there's a huge, spherical shell of icy debris called the Oort cloud. It's the origin point for most of the long-period comets that occasionally swing through and put on a show for us. These comets are the leftovers from the solar system's formation, and they're just sitting out there, frozen, waiting for something to nudge them. Sometimes a passing star or a galactic tide gives them a little push, and they fall inward, screaming toward the Sun. And if one of those comets happens to get its trajectory just right, it could slam into Earth. It's happened before. The dinosaurs can tell you all about it. But what if Planet 9 is out there acting like a cosmic shepherd? Its immense gravity could deflect those incoming comets, altering their orbits just enough to send them harmlessly into the void or into the Sun, rather than toward us. It would be a gravitational shield, a silent guardian. Now, no one knows for sure if that's happening. But the math suggests that a planet of that size, sitting in that particular orbit, would have a measurable effect on the trajectories of Oort cloud objects. It could be the reason we're still here, the reason life on Earth hasn't been wiped out by a regular cosmic bombardment. It's a humbling thought, that a planet we've never even seen might be protecting us from a fate we can't even imagine. But let's get to the fourth implication, because this is where the dreamer in all of us wakes up. If Planet 9 is real, it opens up a whole new frontier for exploration. And I'm not talking about sending a little rover. I'm talking about the most ambitious deep space mission ever attempted. A probe to Planet 9, even with our best current technology, would take somewhere between 50 and 100 years to arrive. Let that sink in. That's a lifetime. You could propose the mission today, work on it for a decade, launch it, and then die of old age before it even gets there. Your grandchildren might be the ones to see the first images come back. It would be a mission that spans generations, a legacy project that outlasts any single person involved. And the engineering required is insane. We're talking about a spacecraft that would need to operate for a century, or longer, in the total blackness of deep space. It would need a power source that doesn't degrade, a communication system that can whisper a signal across a distance that makes the Voyager probes look like they're just next door. But it's possible. We have the technology, or we could develop it, and the payoff would be staggering. Imagine the first images of a new planet, a super-Earth, a world lit by a sun that is just the brightest star in an otherwise black sky. Imagine measuring its atmosphere, its composition, its weather. Imagine finding out if it has moons or rings, or even the faintest, most frozen hint of an ocean. It would be the greatest discovery since Galileo pointed his telescope at Jupiter. And it would prove that we are a species that doesn't just stay home. We reach out, we explore, we endure. And then we have to step back and ask the fifth implication, which is a messy one. It's about language. It's about definitions. It's about that word we all think we understand. Planet. If Planet 9 is real, and it's a super-Earth, then the demotion of Pluto looks even more arbitrary than it already does. Remember the whole Pluto drama? In 2006, the International Astronomical Union voted to strip Pluto of its planetary status. They said a planet has to orbit the Sun, it has to be round from its own gravity, and it has to have cleared its orbit of other debris. Pluto failed the last test, so it was kicked out, and a lot of people were furious. But now think about Planet 9. It orbits the Sun, it's round, and at its enormous distance it has almost certainly cleared its orbit, so by those rules it would absolutely be a planet. But then you have to ask, what does that make Pluto? If a planet is defined by its size, by its mass, then Planet 9 is the ultimate example, a world that rules its realm. And yet, Pluto is just a tiny ice ball in a crowded neighbourhood. But if you can have a super-Earth at the edge of the solar system, it breaks the neat categories we've tried to impose on the cosmos. It reminds us that nature doesn't care about our definitions. Nature just does what it does, and we're left scrambling to find words for it. It would make the textbooks harder to write. It would make the arguments at astronomy conferences get a little more heated. And honestly, that's a good thing. It means we're learning. It means we're staying humble. One scientist, Dr. Constant Batygin, one of the main researchers hunting for Planet 9, put it this way. He said, and I'm paraphrasing here, that the discovery of Planet 9 would be the most monumental find in our solar system in over a century. It would rewrite the textbooks. It would change how we view our place in the universe. And that's not an exaggeration. Think about it. We've gotten arrogant. We've looked at our solar system and thought, okay, we've got a pretty good handle on this. We know the planets, we know the asteroids, we know the comets. We've mapped the whole thing. But a super-Earth hiding in the darkness? It's a cosmic reality check. It says that we are not as smart as we think we are. There are secrets out there, right in our own backyard, that we haven't even begun to imagine. And that's a beautiful, humbling, terrifying thought. Because here's the thing. We talk about exoplanets all the time. We've found thousands of them orbiting other stars. We've found super-Earths, mini-Neptunes, hot Jupiters, and even planets that orbit at the exact right distance for liquid water. We talk about them like they're normal, like discovering new worlds is just another Tuesday for astronomers. But the moment we find a super-Earth in our own solar system, everything changes. It becomes personal. It's not a distant point of light in a galaxy far, far away. It's our neighbour, it's part of our home. And that forces us to re-evaluate what we mean by the word home. So, let's sit with that for a second. Let's imagine waking up one morning and seeing a headline that says astronomers confirm a new planet in our solar system. Imagine the chaos, the joy, the debates. Imagine the flood of funding for new missions. Imagine the artists' renderings, the speculation about its surface, its weather, its secrets. It would be a new chapter in human history, a new era of exploration, a reminder that the frontier never closes, it just moves farther out. But all of this hangs on one simple fact: we have never actually seen it. And so we return to that cold, dark frontier, the Kuiper Belt, a cosmic graveyard of icy relics, orbiting in the quiet long after the party of the solar system's formation ended. We talked about those 6 objects, the original 6, whose strange clustered orbits first whispered the name Planet 9 into the ears of astronomers Mike Brown and Konstantin Batygin. But the story didn't end there. That whisper has grown into a persistent nagging voice. Because once you know what to look for, you start seeing the pattern everywhere. Let's fast forward to the year 2018. Astronomers are scanning the sky, as they always do, and they find something. It's catalogued as 2017 OF201. Catchy name, right? But this isn't just another space rock. This is a dwarf planet candidate, a world about 700 kilometers across. To put that in perspective, that's roughly half the size of Pluto, a significant chunk of ice and rock. And when they plotted its orbit, something clicked. It wasn't just orbiting out there in a random chaotic path. It was falling into line. Its orbit sheared off at an angle, its path stretched out into a long elliptical loop, and it slotted neatly into the same strange alignment as those original 6 objects. It was like finding a 7th suspect in a lineup who matches the exact same description. The odds of this being a coincidence were getting slimmer by the minute. This is where we have to start talking about a concept called shepherding. It sounds pastoral, almost gentle, like a border collie guiding a flock of sheep. But in the cold mechanics of space, shepherding is a brutal gravitational ballet. The computer models that Brown and Batygin run show us how it works. Imagine a massive hidden planet out there, a dark giant sitting in the deep freeze. It doesn't have to be close to these smaller Kuiper Belt objects to influence them. It just has to be big. Over millions of years, its gravity tugs at these smaller icy bodies, gently nudging them, herding them. It pulls their orbits into a specific coherent shape. It tilts them. It organizes them. Without that massive shepherd, these objects should have random, widely dispersed orbits. They should be a mess. But they aren't. They are lined up. It's the most compelling piece of circumstantial evidence you could ask for. It's the gravitational fingerprints of something huge. This brings us to a model, a story that astronomers tell about our solar system's wild youth. It's called the Nice model, named after the city in France where it was first developed, and it is a story of chaos. The Nice model suggests that the early solar system wasn't the neat, orderly place we see today. Oh no, in the first billion years or so, the giant planets, Jupiter, Saturn, Uranus and Neptune, didn't just sit where they are now. They migrated. They moved. Imagine a game of cosmic billiards played over hundreds of millions of years. Jupiter, the heavyweight champion, would swing in, its gravity scattering smaller bodies like a bowling ball through pins. These planetesimals, these building blocks of planets, were flung every which way. Some crashed into the inner planets. Some were thrown out into the Oort cloud, and some were pushed completely out of the solar system, becoming orphans in the dark between the stars. But here's where the Nice model gets really interesting for our story. Some simulations of this chaotic migration suggest that there wasn't just 4 giant planets at the start. There may have been 5, a 5th giant, a world of ice and gas, born alongside Jupiter and Saturn, a world that was in the wrong place at the wrong time. As Jupiter and Saturn danced their gravitational waltz, a migration dance that was unstable and violent, this fifth giant got caught in the mosh pit, and the big guys did what they do best. They threw a punch, a gravitational punch so powerful that it flung this proto-giant planet out of the inner solar system entirely. Here is the elegant part. This ejected giant hypothesis does something that no other theory has managed. It explains a major hole in our understanding of the solar system. Why don't we have a super-Earth? You know, those planets that seem to be everywhere else in the galaxy. Rocky worlds 2 to 10 times the mass of Earth. Our solar system is weird. We have small rocky planets, then giant gassy planets, and then nothing in between. We seem to be missing a piece. The ejected giant theory says that piece is there. It's just not in the living room anymore. Our missing super-Earth was that fifth giant. It got pushed out during the chaos, shoved into a distant, cold, stable orbit. An orbit that sits exactly where Planet 9 is predicted to be. It is a breathtakingly elegant idea. The thing we thought was missing wasn't destroyed. It was banished. It's still out there, somewhere, in the cold. This idea, this convergence of evidence, is why the case for Planet 9 is so strong in the minds of its proponents. It's not just about odd orbits anymore. It's about a coherent, plausible story of how our entire solar system evolved. It's about a missing chunk of our own history. And the man who started it all, Mike Brown, is more convinced than ever. In 2024, he didn't hedge his bets. He walked right up to the line and stood there. In a public statement, he said, and I'm paraphrasing the spirit of it here, that he finds it very unlikely Planet 9 does not exist. Those were his words. Very unlikely. He argued that there is no alternative explanation, no other reasonable hypothesis, that accounts for all the observed effects. Not just the clustering of the Kuiper Belt objects. Not just the tilting of the plane. But the way comets come in from the outer system, the way the orbits of distant objects are sheared off. He says the signal is too strong, too consistent to be a coincidence. But here we are, standing on the edge of a massive contradiction. And this is the part that should make you feel the tension in the room. Every single piece of evidence I have just described is indirect. All of it. There is no photograph. There is no spectral signature telling us what the planet is made of. There is no confirmation of any kind that a telescope has blinked and seen a faint moving dot in the darkness. The evidence is all about gravitational cause and effect. It's about seeing the wind blow the leaves, but never seeing the wind itself. It's about hearing footsteps in the hallway of an empty house, but never seeing the person walking, that gap, that vast, uncomfortable, maddening gap. Between strong circumstantial evidence and zero direct proof is where the real mystery lives. You can have 100 smoking guns, but if you don't have the body, you don't have a closed case. You have a mystery. You have a story of speculation. You have a hypothesis that, for all its elegance, remains untested by the one thing that matters most, a direct detection. It's like being a detective who has the perfect suspect, the motive, the means, the opportunity. All the puzzle pieces fit, but the suspect has no name, no face, and no address. You can feel their presence, you can trace their impact on the world, but you cannot point at them and say, there they are. And this brings us to the other side of the coin. Because science is not a monolith. It is a messy, argumentative, beautiful brawl of ideas. And not every astronomer is convinced. In fact, some of the most respected scientists in the field have stood up and said, hold on a second, let's slow down. They argue that the entire Planet 9 hypothesis is built on a statistical mirage. They look at the same data and see something different. They see a small sample size. They see selection bias. They argue that astronomers who are looking for a planet in a specific part of the sky are more likely to find objects there, because that's where they're pointing their telescopes. It's a self-fulfilling prophecy. They say the clustering of orbits is a trick of the light, a product of how we observe, not a real physical signal. They see a handful of objects, maybe a dozen or two, that follow a pattern. But they argue that with the thousands of undiscovered objects floating out there in the Kuiper Belt, these few are just coincidental outliers. The equivalent of seeing a few heads in a row when you flip a coin and declaring the coin is rigged. They point to the fact that the sky is big, really big, and our surveys are still shallow. We have a very biased view of what's out there. They say that before we invent a whole new planet to explain a pattern we think we see, we should first be absolutely sure that the pattern is real, and not just a trick of our incomplete vision. They are the voices of caution, the ones who remind you that in science, the most elegant hypothesis is not always the correct one. The most elegant hypothesis is often the one that is most appealing to our human desire for a clean, satisfying story. But the universe is rarely clean. It is messy. It is full of noise. And sometimes that noise looks like a signal until you listen a little closer. So we find ourselves in a fascinating standoff. On one side, you have overwhelming circumstantial evidence and a compelling, elegant story of the solar system's violent past. On the other side, you have the hard, cold vacuum of direct proof. You have the skeptics who see a statistical illusion and a tendency to see patterns where none exist. It is the perfect scientific mystery. It is a 30-year-old cold case with a suspect who leaves footprints everywhere but refuses to show their face. The search continues. The telescopes are still pointed at the dark. The computers are still crunching the data. And somewhere out there, in that silent, unimaginably cold region beyond Neptune, something is pulling the strings. Something is making the distant wanderers of the Kuiper Belt dance to its tune. Whether it is a planet, a statistical ghost, or something else entirely, we are watching, we are waiting, and we are a little bit scared, because the alternative to Planet 9 is a universe that is even stranger than we thought. We stand, then, in that cold, dark frontier, not just as scientists, but as inheritors of a long tradition of looking for ghosts in the machine. The tension between the circumstantial and the direct is the engine of discovery. It's what pushes us to build better telescopes, to stare longer, to think harder. And the story of Planet 9 is in many ways a story about how we see. It's a story about the limits of our senses and the audacity of our inferences. To understand how we got here, we have to rewind the cosmic clock, not to the formation of the solar system, but to the dawn of modern astronomy. The discovery of Neptune itself is the blueprint for this entire drama. In the early 1840s, the planet Uranus was behaving badly. It was not following the path that Newton's laws predicted. It was straying, wobbling, as if something were tugging on it from the dark. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently did something extraordinary. They didn't look through a telescope. They picked up a pen. They used the mathematics of gravity to predict the existence of an unknown planet, based solely on the perturbations of Uranus's orbit. They calculated where it should be, what mass it should have, and what path it should follow. Then they told the astronomers where to point their telescopes, and on September 23, 1846, Johannes Galler, a German astronomer, looked exactly where Le Verrier said to look, and there it was, a faint bluish disk, Neptune, found not by sight but by mind, found by its gravitational ghost. That is the template. That is the dream that drives the search for Planet 9. It was the first time a planet was discovered not by accidental observation, but by mathematical prediction. It was a triumph of inference over direct observation. It proved that gravity is a language that the universe speaks, and that we can learn to listen. Every time an astronomer today plots the orbit of a distant Kuiper Belt object and sees it sheared off at an angle, they are hearing an echo of that same language. They are hearing the whisper of a mass that they cannot see. But history is also a teacher of caution, because the Neptune story has a dark mirror. A few decades later, in the late 19th century, the same thing happened again. Mercury, the innermost planet, was also wobbling. Its orbit was precessing, shifting slowly over time, in a way that Newton's laws, even accounting for the pull of all the known planets, could not explain. So, naturally, astronomers looked for another ghost. A planet inside the orbit of Mercury. They even named it Vulcan. Le Verrier, The hero of the Neptune story dedicated years of his life to searching for it. He believed in it with absolute conviction, and why not? The method had worked once. It should work again, but Vulcan did not exist. The wobble of Mercury was not caused by a hidden planet. It was caused by something far more revolutionary. It was caused by the fact that Newton's laws of gravity were incomplete. In 1915, Albert Einstein published his theory of general relativity, and it explained Mercury's wobble perfectly. Gravity, Einstein showed, is not a force in the Newtonian sense. It is a curvature of space-time. And close to a massive body like the Sun, that curvature warps the path of a planet in a way that Newton never predicted. The ghost of Vulcan was not a planet. It was a sign that our fundamental understanding of the universe was wrong. This is the cautionary tale that hangs over the search for Planet 9. The skeptics are not being stubborn. They are being historically aware. They remember Vulcan. They know that a gravitational anomaly can point to a new planet, or it can point to a new physics. When we see the clustered orbits of the Kuiper Belt objects, we must ask ourselves, are we seeing the gravitational pull of a hidden giant? Or are we seeing something even stranger? Could our model of gravity be incomplete on the largest scales? Could there be a modification to Newtonian dynamics, something like modified Newtonian dynamics, or MOND, that explains the clustering without a planet? It's a long shot, but it's a question that must be asked. The ghosts of Vulcan demand it. Yet the proponents of Planet 9 have a powerful counter-argument. They look at the pattern, and they see something that the Vulcan hunters never had. Vulcan was inferred from a single anomaly, the wobble of one planet, Mercury. It was a single data point. The Planet 9 hypothesis is built on multiple, independent and converging lines of evidence. It's not just that the 6, or now 7, or now 12, or now more, Kuiper Belt objects are clustered in one part of the sky. It's that their orbits are also tilted. It's that their perihelia, the point in their orbit closest to the Sun, are all sheared off in the same direction. It's that there is a population of objects with almost perpendicular orbits, orbiting nearly at right angles to the plane of the solar system. It's that the plane of the entire distant Kuiper Belt itself is slightly warped. Each of these anomalies taken alone could be a statistical fluke or a bias of observation. But taken together, they form a pattern that is incredibly hard to explain without a single, massive gravitational shepherd. It's like finding a room full of clocks that all read the same wrong time. One clock might be broken, but if all of them are off by the exact same amount, you start to suspect that someone has been resetting them. And then there is the question of the missing mass. The solar system has a strange emptiness. Between the orbit of Neptune and the inner edge of the Oort cloud, there is a vast gap. We have found some objects like the inner Kuiper Belt, but they are relatively small. The total mass of all the material in the Kuiper Belt is estimated to be only a few % of the mass of Earth. That seems too low. It seems like a cosmic vacuum. The nice model, the story of the chaotic migration of the giant planets, actually predicts that this region should have been cleared out. The planets, as they migrated, would have flung most of the material inward or outward. But the model also predicts that there should be a remnant, something that was too big to be flung away, something that settled into a stable, distant orbit. That something in the model is the missing fifth giant, a world with a mass between 5 and 10 times that of Earth, a world that is not a gas giant like Jupiter, but an icy super-Earth, a world that is dark, cold, and incredibly faint. This brings us to the great irony of the search. The very thing that makes Planet 9 so compelling, its distance, is the thing that makes it so hard to find. It is not close. It is not bright. It is a frozen, dark world orbiting hundreds of times farther from the Sun than the Earth is. The Sun, from that distance, is not a blazing ball of light. It is just a very bright star, a point of light in a sky that is forever black. Planet 9, if it exists, is not hot enough to glow in infrared. It is not generating its own light. It is a dark rock, reflecting a tiny fraction of the feeble sunlight that reaches it. Its apparent magnitude, the measure of its brightness as seen from Earth, is predicted to be extremely faint. Brighter than the faintest objects we have found in the Kuiper Belt, but still incredibly dim. It is like looking for a charcoal briquette in a coal cellar at midnight. The search has become an exercise in patience and technological brinkmanship. The largest telescopes on Earth, like the Subaru telescope on Mauna Kea in Hawaii and the Victor M. Blanco telescope in Chile, have been scanning the sky for years. They have covered vast swaths of the predicted orbital path. They have found thousands of new objects: comets, asteroids, small worlds, but not the planet. Each time a survey fails to find it, the allowed orbital parameters shrink. The astronomers can say, well, it cannot be in this part of the sky, and it cannot be that bright. They are slowly, systematically excluding possibilities. They are methodically eliminating the places where it is not. This is the scientific process at its most grindstone. It is not glamorous. It is a slow, painstaking elimination of the darkness. And then there is the Vera C. Rubin Observatory, currently under construction in Chile. When it comes online, it will become the most powerful survey telescope ever built. It will scan the entire visible sky every few nights for a decade. It will produce a time-lapse movie of the universe. It will find millions of new objects, including, perhaps, the faint, slow-moving dot that is Planet 9. If Planet 9 exists, the Rubin Observatory is almost guaranteed to find it within the first year or two of its operation. It is our best bet. It is our brightest hope. The entire astronomical community is holding its breath, waiting for that first light. But what if it doesn't? What if the Rubin Observatory scans the entire sky, finds everything that moves, and Planet 9 is not there? That would be a devastating result for the hypothesis. It would not prove that Planet 9 does not exist, because the observatory has limits. It might be too faint, too far away, or moving too slowly to be detected. But it would push the allowed parameter space to an extreme. It would make the hypothesis less and less likely, and at some point, a threshold is crossed. At some point, the statistical arguments that support Planet 9 begin to break down. At some point, the skeptics' voices grow louder. At some point, the search for a single large planet might give way to a different idea entirely. And that is where the story gets really strange. Because there is another hypothesis, one that is even more unsettling than a hidden planet. What if the clustering of the Kuiper Belt objects is not caused by a single massive body, but by a population of dark, dense objects? What if there is not one Planet 9, but a swarm of them? This is the idea of a primordial black hole, a black hole that is not the corpse of a massive star, but a tiny ancient relic from the Big Bang. These so-called primordial black holes, if they exist, could have the mass of a planet, but be smaller than a grapefruit. They would be invisible. They would be completely dark. They would not reflect any light, but they would have gravity. And a single primordial black hole, orbiting in the outer solar system, would produce exactly the same gravitational effects as a planet. It would tug on the Kuiper Belt objects, herd them into clusters and tilt their orbits. It would be a ghost of a different kind entirely. A ghost that is a singularity. This idea is not mainstream. It is speculative, exotic, and far more difficult to prove than a planet. But it is a reminder that the search for Planet 9 is not just a search for a world. It is a search for the truth, whatever that truth may be. It is a search that pushes us to the edge of our knowledge and then asks us to go a little further. We are standing in the dark, pointing our instruments at the void, and asking the universe to show us its secrets. The answer will come. It always does. But the waiting, the uncertainty, the tension between belief and proof, that is the crucible of discovery. And we are in it right now, together. Not everyone is convinced. In fact, a significant and vocal minority of astronomers have spent the last decade pushing back against the Planet 9 hypothesis with increasing force. These are not contrarians looking for a fight. These are respected scientists who look at the same data and see something very different. They see a mirage. They see the human mind doing what it does best, finding patterns where none exist. They see a story we have told ourselves because the alternative, that the outer solar system is just messy and random, feels too unsatisfying. The core criticism is brutally simple, and it hits at the very foundation of the original claim. That initial batch of 6 objects, the ones with the strange and tilted orbits that started the whole hunt, the sample size was laughably small, 6 objects, out of thousands upon thousands of known Kuiper Belt objects. Imagine walking into a stadium with 80,000 people, talking to 6 of them, and then declaring you know the political opinions of the entire crowd. That is the scale of the leap we are talking about. The universe is noisy, space is chaotic, and 6 data points are not a conspiracy. They are a whisper at a rock concert. The real challenge came in the year 2020. That was the year the skeptics sharpened their knives and went to work. 2 massive independent surveys decided to test the clustering claim in a way that had never been done before. The first was the Outer Solar System Origins Survey, known as OSSOS. This team did not just go looking for a few interesting objects. They catalogued over 800 distant trans-Neptunian objects. 800! That is an enormous leap from 6. The second survey came from the Dark Energy Survey, which added another 316 objects to the known population. Together, these 2 studies essentially said, give us the full picture, not just the highlights. And when they looked at that full picture, something very troubling emerged. Both surveys adjusted for something called observational bias. This is a concept that sounds dry, but is actually the difference between seeing the truth and seeing what you want to see. Observational bias is the simple, maddening fact that telescopes do not see the sky evenly. They see specific directions. They see at specific times. They see through the haze of our own galaxy. If you spend more time looking at one patch of sky, you will naturally find more objects there. That does not mean those objects are clustered by some hidden giant. It means you looked there more. When the OSSOS and Dark Energy Survey teams accounted for this bias, when they mathematically stripped away the illusion of human error, the orbital clustering vanished. It did not just shrink, it disappeared. The pattern that had launched 1,000 headlines and a global hunt for a 9th planet turned out to be a ghost in the machine. The data did not lie, but the way we collected that data was lying to us. Samantha Lawler, an astronomer at the University of Regina, and a key voice in the skeptical camp, did not mince words. She stated plainly that the original hypothesis, as presented, does not hold up to detailed observations. When you control for where and when you are looking, the anomaly goes away. It is as simple and as devastating as that. Then there is astrophysicist Ethan Siegel, a writer and researcher who has followed this debate closely. He argues that most scientists, when pressed, no longer believe Planet 9 is real. He points directly at observational bias as the root cause of the confusion. We saw a pattern because we were only looking in the places where we expected to see one. Let me make sure this is clear because it matters. Imagine you are standing in a field at night with a flashlight. You only shine the flashlight to your left. After 10 minutes, you notice there are a lot of fireflies on your left. You say, wow, all the fireflies are gathered in that direction. There must be a reason. A big firefly queen or something. But you never checked your right. You never checked behind you. You just looked where the light was. That is observational bias. Our telescopes, sensitive as they are, have spent decades scanning the same favourite patches of sky, especially near the plane of the Milky Way where the stars are thickest. And in that dense star field, faint objects are incredibly hard to pick out. The result is a map of the outer solar system that is not a true census. It is a badly distorted selfie. Samantha Lawler described the challenge of detection in terms that make you feel the frustration. She says searching for these objects is like trying to find a small, faint, moving dot among a sea of billions of stars. Not dozens, not hundreds, billions. Every single night, astronomers look at images filled with points of light, and they have to decide which one is moving, which one is close, which one matters. Human error is inevitable. Bias is baked into the process, and when you do not account for that, you get a fake planet. Then there is the statistical argument, and this one is a real gut punch. Planetary scientist Hal Levison ran the numbers on the ejection scenario. The idea is that Planet 9 was a giant planet, probably ejected from the inner solar system billions of years ago, by a close encounter with Jupiter or Saturn. It got kicked out, flung into the dark, and somehow found a stable orbit at the edge of the system. Leveson asked a simple question: how likely is that? His answer was not encouraging. The probability of an ejected giant settling into a stable distant orbit is only about 2%. That is a very long shot. For that to happen, you would need dozens of other objects to have been ejected at the same time, flung out and lost forever. Where are the traces of those lost worlds? Where is the debris? Where is the chaos that should have accompanied such a violent event? The solar system is messy, but it is not that messy, not without leaving some evidence. In 2017, planetary scientist Catherine Volk offered a counter-hypothesis. She suggested that maybe the answer was not a massive planet far away, but a smaller world much closer in. She proposed a Mars-sized object hiding right inside the Kuiper Belt, closer to us than Planet 9 would be. It was a clever idea. It explained some of the weird orbital quirks without requiring a super-Earth at the edge of nowhere. But then new data came in. More observations, more surveys, and her own model began to crack. The signals she thought she saw did not hold up. She has since grown skeptical of her own proposal, and she gave one of the most honest and refreshing assessments I have heard from any scientist in this debate. She said, and I quote, "I do not think any of the existing predictions are correct. Think about what that means." One of the people who actually tried to solve the mystery with a different model, who offered an alternative, who put her reputation on the line, is now telling us that she thinks everyone is probably wrong. Not just the Planet 9 believers, not just the skeptics, everyone. The field is so confused, the data so ambiguous, and the biases so tangled that no one has cracked it yet. So here we are, a decade into the search, billions of dollars worth of telescope time, thousands of papers, dozens of proposed orbits. And what do we have? A stalemate. A field that is genuinely split down the middle, with passionate, intelligent, world-class scientists on both sides. On one hand, you have the circumstantial evidence, the strange tilts of some Kuiper Belt objects, the unexplained clustering of distant orbits, the lingering suspicion that the solar system is too orderly for this to be random. On the other hand, you have the statistical doubts that will not go away, the small sample sizes, the observational biases, the vanishing patterns when you account for human error, the gut feeling, shared by many, that we are chasing shadows. The truth is painfully simple. We have not found it, we have not ruled it out. And until we have a new kind of evidence, a telescope that can see deeper, a survey that covers the entire sky without blind spots, a detection that is undeniable, we are stuck. We are standing in the dark, pointing our instruments at the void, and asking the universe to show us its secrets. The answer will come. It always does. But the waiting, the uncertainty, the tension between belief and proof, that is the crucible of discovery. And we are in it right now, together. The tension in this field has now become a defining characteristic of modern planetary astronomy. It is a discipline that prides itself on prediction, on the elegance of mathematics, on the ability to find a world before you ever lay eyes on it. That is the legacy of Neptune. In the 1840s, mathematicians Urbain Le Verrier and John Couch Adams independently looked at the orbit of Uranus, saw that it wobbled in ways that Newton's laws could not explain, and concluded that an unseen planet must be pulling on it from beyond. They did not have a telescope pointed at the sky. They had a pen, a piece of paper, and a profound faith in the laws of physics. And they were right. When astronomers finally pointed their telescopes to the coordinates Le Verrier had calculated, Neptune was there, almost exactly where he said it would be. It was the greatest triumph of celestial mechanics in the 19th century. It proved that the universe was knowable, that gravity was a language we could read, that we could find worlds in the dark. That triumph has haunted us ever since. Every generation since Neptune has tried to find its own version of that story. In the early 20th century, astronomer Percival Lowell became obsessed with the idea that another planet, which he called Planet X, was disturbing the orbits of Neptune and Uranus. He searched for years, funded his own observatory, and died without ever finding it. 14 years after his death, in 1930, Clyde Tombaugh discovered Pluto at the Lowell Observatory. It was hailed as the discovery of Planet X, but it was not. Pluto was tiny. It could not possibly have caused the orbital perturbations Lowell had predicted. The wobbles, it turned out, were an illusion caused by an overestimation of Neptune's mass. For decades, humanity thought we had found a giant. We had found a pebble. Then in the 1970s and 80s, another ghost emerged. Astronomers observed that comets seemed to come from a vast reservoir beyond the planets, a hypothetical cloud named after Jan Oort. The orbits of some comets seemed to be aligned in a way that suggested a distant planetary body was shepherding them. Some astronomers proposed a world they called Nemesis, a dark companion to our Sun, a Death Star that would periodically send comets hurtling toward Earth, causing mass extinctions. It was a sensational idea. It captured the public imagination. It was also wrong. Better data, wider surveys, and more careful analysis showed that the clustering of comet orbits was a statistical artifact. There was no Nemesis. There was no Death Star. There was just noise. Every generation reaches for the ghost in the machine, and every generation so far has come up empty. The search for Planet 9 carries the weight of all those failed predictions. It is the latest verse in a very old song. The believers will tell you that this time is different. The technology is better. The data is more comprehensive. The models are more sophisticated. The skeptics will tell you that we have heard that before. They will point to Lowell and his obsession. They will point to Nemesis and its dramatic but hollow narrative. They will tell you that the human mind is a pattern-matching engine, and it is too good at its job. We see faces in clouds, we see animals in constellations, we see planets in noise. Let me give you a deeper look at the evidence that keeps the believers going, despite all the skepticism. Because they are not irrational, they have real data. Consider the object known as Sedna. Discovered in 2003, Sedna is one of the most distant known objects in the solar system. Its orbit is eccentric and elongated, taking it from about 76 astronomical units at its closest to the Sun to over 900 astronulicals at its farthest. For context, 1 AU is the distance from Earth to the Sun. Pluto orbits at about 39 astronomical units. Sedna goes out more than 20 times farther, and its orbit is tilted. It never comes close enough to Neptune to have its path significantly altered by that planet's gravity. So, how did Sedna get there? What put it on that strange, lonely road? The standard model of solar system formation does not easily explain it. Planet 9 does. A massive distant planet could have kicked Sedna into that orbit and left it there like a bowling ball scattering pins. Then there is the clustering itself. Even after the OSESOS and dark energy survey results, even after the bias corrections, some signals remain stubborn. The objects with the most extreme orbits, the ones that stay farthest from Neptune's influence, still show a slight preference for being aligned in one direction. The signal is weaker than originally claimed. It is not the screaming siren it once was, but it is not zero. It is a whisper, and a whisper is enough to keep a hypothesis alive, especially when the stakes are so high. One detection would change everything. One single observation of a faint, moving dot in the outer darkness would transform the whisper into a roar. That is what keeps astronomers going back to the telescope, night after night. That is what keeps the papers flowing. That is what keeps the dream alive. The search itself has become a story of technological endurance. Astronomers have used some of the most powerful instruments on Earth and in space. The Subaru telescope in Hawaii, with its giant 8-meter mirror and its wide-field camera, has been a workhorse. It scans vast swaths of the sky, looking for the faint, slow movement that betrays a distant world. The Cerro Tololo Inter-American Observatory in Chile has joined the hunt. The Zwicky Transient Facility in California has added its eyes. And then there is the Legacy Survey of Space and Time, the LST at the Vera C, Rubin Observatory in Chile. This telescope, when it reaches full operational capacity, will be the most powerful survey instrument ever built. It will image the entire visible sky every few nights, creating an unprecedented movie of the cosmos. It will see things we have never seen before. and many astronomers believe that LSST will be the instrument that finally settles the Planet 9 question one way or another. If Planet 9 is out there, LSST will find it. If it is not, LSST will rule it out with a level of certainty that no previous survey has achieved. That is the promise, that is the hope. But the LSST has faced years of delays, budget constraints, technical challenges, the pandemic. It is now expected to begin full science operations in the mid-2020s. But timelines in astronomy are notoriously optimistic. We have been waiting a long time. We may have to wait a little longer. While we wait, the theoretical work continues. Astronomers have refined their models of what Planet 9 should look like if it exists. The original estimate suggested a mass of about 10 Earths. More recent work has pushed that number down, maybe to 5 Earths, maybe to 3. The lower the mass, the harder it is to detect, because a smaller planet reflects less sunlight and is dimmer. The orbit is also uncertain. The best guesses place it at somewhere between 200 and 800 astronomicals from the Sun, with an orbital period of 10 to 20,000 years. That is a long time to wait for a repeat performance. The orbit is likely tilted relative to the plane of the solar system, which would explain why it has been so hard to find. We have been looking in the wrong places. There is also the question of how Planet 9, if it exists, formed and survived. The leading theory is that it started closer to the Sun, in the same region where Jupiter and Saturn formed, and was ejected by a close gravitational encounter. But as I mentioned, the probability of it settling into a stable distant orbit is low. That has led some astronomers to propose alternative formation mechanisms. Maybe it was not ejected from the inner solar system. Maybe it was captured from another star. The Sun was born in a cluster of stars, a dense nursery where close encounters were common. It is possible that a rogue planet from a neighbouring star system was gravitationally stolen by our Sun and flung into the outer darkness. That scenario is even more speculative, but it is not impossible. We know that rogue planets exist. We have detected them floating through interstellar space. We know that star clusters are chaotic places. The ingredients for capture are there. We just do not know if the recipe was ever followed. The debate has also expanded to include the possibility that the clustering is caused not by a single large planet, but by a swarm of smaller objects. Perhaps there is a dense disk of icy bodies beyond the Kuiper Belt, too faint to see individually but massive enough, collectively, to perturb the orbits of the ones we can detect. This is sometimes called the shepherding disk hypothesis. It is elegant in its simplicity. It does not require a single giant world that we have somehow missed. It only requires that our census of the outer solar system is incomplete, which we know it is. The problem is that the mass required to explain the observed clusterings is substantial. You would need a disk with a mass comparable to Earth, spread out over hundreds of AUU. That is a lot of ice and rock. We have no direct evidence that such a disk exists, but we have no direct evidence that it does not. Then there is the possibility that the clustering is real, but caused by something even more exotic. Some have speculated about a primordial black hole, a tiny remnant from the early universe, lurking in the outer solar system. A black hole with the mass of a few Earths would be compact, dark, and nearly impossible to see. It would reveal itself only through its gravitational influence on surrounding objects. That is a wild idea. It is also not impossible. Primordial black holes have been theorized for decades. They have never been detected. But if one were found in our own solar system, it would be the most revolutionary discovery in physics since the detection of gravitational waves. It would rewrite our understanding of dark matter, of the early universe, of the very nature of reality. The probability is vanishingly small, but it is not zero. And in a field where we have been wrong so many times before, even the impossible deserves a second look. The psychological dimension of this search cannot be overstated. Human beings are terrible at uncertainty. We crave closure. We want the answer. We want to know if there is a ninth planet or if there is not. The prolonged ambiguity is agonizing. It creates camps. It creates loyalty. It creates a kind of tribalism that is antithetical to the scientific method. I have seen astronomers roll their eyes at the mention of Planet 9. I have seen others defend it with a fervour that borders on religious. That is not a criticism. It is a description. When you spend years of your life searching for something, when you stake your reputation on a hypothesis, when you write papers and give talks and apply for grants, it becomes personal. You cannot separate the science from the scientist. And that emotional investment can distort judgment. It can make you see patterns that are not there. It can make you dismiss contradictory evidence. It can make you double down when you should reconsider. The skeptics, for their part, are not immune to their own biases. There is a certain intellectual satisfaction in being the one who punctures the balloon. There is prestige in being the voice of caution, the one who warns against overreach, the one who reminds everyone that we have been fooled before. The skeptics have history on their side. Every previous search for a hidden planet except Neptune has ended in disappointment. That track record is powerful. It is also a form of bias. The past does not guarantee the future. Just because we have been wrong before does not mean we are wrong now. But it does mean we should be humble. It does mean we should demand extraordinary evidence for extraordinary claims. I want to give you a sense of what it actually looks like to search for Planet 9. This is not a glamorous process. It is not like the movies where a lone astronomer looks through an eyepiece and gasps. It is slow. It is tedious. It is data reduction. It is writing code to subtract the background stars. It is staring at millions of faint dots and trying to find the one that has moved. It is false positives. It is dead ends. It is nights of observing that yield nothing. It is sleepless days spent analysing images that show only emptiness. The search for Planet 9 is not a quest. It is a job. A frustrating, obsessive, beautifully human job. Astronomers use a technique called shift and stack. They take multiple images of the same patch of sky, taken hours or days apart. They then shift the images relative to each other to compensate for the motion of a hypothetical planet, and they stack them on top of each other. The signal from a moving object adds up. The static background stars blur into noise. It is a clever technique. It is also computationally intensive. And it requires you to know, or at least guess, the direction and speed of the planet's motion. If you guess wrong, you miss it. If you guess right, you might find a faint dot that has never been seen before. It is like searching for a needle in a haystack, except the haystack is the entire sky, and the needle is moving, and you do not know what colour it is, or how big it is, or even if it is really there. The emotional rhythm of this search is brutal. You have moments of hope. A candidate object appears. You check the data. You cross-reference with other surveys. You hold your breath. Maybe this is it. Maybe this is the one. And then you realise it is a known asteroid, or a cosmic ray hit on the detector, or an artifact of the data processing. The hope deflates. You go back to the beginning. You do it again and again and again. That is the reality. That is the search. And that is why the debate continues. Because no one has found it. But no one has proven it does not exist. We are suspended in a state of not knowing, and that is the hardest place to be. It demands patience. It demands intellectual honesty. It demands that we hold two contradictory ideas in our heads at the same time, that Planet 9 could be real, and that Planet 9 could be an illusion. We must be open to both possibilities. We must follow the evidence wherever it leads, even if it leads nowhere. The solar system is vast. It is dark. It is cold. It is full of secrets we have not yet uncovered. Every generation of astronomers has thought they had mapped it completely. Every generation has been wrong. There are objects out there we have not seen. There are worlds we have not dreamed of. Planet 9 may be one of them, or it may be the latest in a long line of ghosts. We do not know yet, but we are searching. And that search, in all its frustration and uncertainty and silent hope, is one of the most human things we do. By the mid-2020s, the debate had reached something close to a standoff, a stalemate. Both sides had sharpened their arguments into razor edges. One camp, the believers, pointed to the strange orbital clustering of certain distant Kuiper Belt objects. The way they all seemed to tilt in the same direction, as if something massive and unseen was herding them like a cosmic sheepdog. They walked you through the math, step by step, showing how a planet with 5 to 10 times the mass of Earth, hiding somewhere between 400 and 800 astronomical units from the Sun, could explain those bizarre alignments perfectly. The other camp, the skeptics, they had their own arguments just as sharp. They pointed out that this so-called clustering could be a simple observational bias. Telescopes, after all, are not equally sensitive across the entire sky. They look where they look, and sometimes the pattern you see is just an artifact of where you decided to point the lens. They argued that our sample size of trans-Neptunian objects was still too small. You cannot claim a planet exists based on the orbits of a handful of icy rocks when you have surveyed barely a fraction of the outer darkness. And so the two sides stared at each other across a gap that neither argument could bridge. Both camps were brilliant. Both had peer-reviewed papers. Both had convinced themselves they were right. And yet, no one could prove it. Not conclusively. Not without new data. The theoretical debate, as elegant and sophisticated as it was, had reached a dead end. It was like two chess grandmasters replaying the same endgame over and over, each one insisting his strategy would win, but neither able to actually make the winning move because, at the end of the day, the game itself was missing a piece. Physics could point the way. Mathematics could draw a map, but only telescopes could find the thing. And the telescope, at least the ones we had in the mid-2020s, were simply not up to the task. Let me make this painfully clear for you. Imagine you are standing on a mountaintop on a moonless night, looking for a single firefly. Only the firefly is not flickering. It is dim, almost cold, and it is floating, drifting slowly, at a distance of 800 times the distance between the Earth and the Sun. And your job is to find it somewhere in a patch of sky that is roughly the size of thousands of full moons. That is the challenge. That is the search space. Most telescopes in operation today, even the big ones, are not sensitive enough to pick up something that's faint and that's slow moving at that distance. A planet at 800 astronomical units would be reflecting sunlight that has already travelled for more than 4 days just to reach it. By the time that light bounces back to us, it is incredibly weak. It is barely a whisper of a photon. You need a massive bucket of a telescope to catch that whisper. You need an observatory like the Keck telescopes on Mauna Kea, with their 10-metre mirrors. You need the Subaru telescope, also on Mauna Kea, with its wide field of view. You need the Hubble Space Telescope sitting above the atmosphere, unbothered by the blurring turbulence of the sky. And even these giants, these crown jewels of astronomy, have to fight for every second of observing time. Time on these instruments is not given freely. It is rationed. It is allocated by committees that receive hundreds of proposals for every slot available. Astronomers submit their best ideas. They beg for a few nights, maybe a few hours, to scan a tiny sliver of this enormous search space. And then they take those images, they compare them against older images. They look for a faint dot that has moved even slightly against the background of fixed stars. It is painstaking work, it is slow work, and it takes years. The search space is simply too big, even with automated surveys, with computers scanning and comparing millions of pixels. It is like trying to find a specific grain of sand on a beach by walking up and down with a magnifying glass. You get tired. You get frustrated. You start to see things that are not there. And that is exactly what happened. Over the years, there were false alarms. A few of them, actually. Every couple of years, a new candidate would pop up. A faint dot on an old survey plate, a barely visible smudge in an infrared image, and the news would spread like wildfire through the astronomy community. Planet 9 found. The headlines would blare for a day or two, and then the follow-up observations would come in, and the dream would crumble. Sometimes it was just a background star, a weird asteroid, a bit of cosmic dust, a glitch in the detector. Sometimes it was a more careful orbital calculation that showed the object was not where it needed to be. One by one the candidates fell. Each time the hope deflated a little more. Each time the skeptics nodded quietly. Each time the believers went back to the drawing board, wondering if they had been looking in the wrong place. One particular false alarm stands out. It happened in 2025. A team of researchers was combing through old archival data from two infrared space telescopes, IRAS and ACARI. IRAS, the infrared astronomical satellite, had scanned the entire sky back in 1983. ACARI, a Japanese observatory, had done the same in the mid-2000s. Both had taken snapshots of the whole celestial sphere, but they had been looking for other things, for star-forming regions, for dusty galaxies, for asteroids. Nobody had gone back to that data with Planet 9 in mind. Until 2025, the team found something. A faint, slow-moving infrared source in both surveys. It was dim, it was moving at a crawl. It was at a distance that, if you did the parallax math, put it somewhere around 500 to 700 astronomical units. The world got excited. This felt different. This felt real. Mike Brown, the man who had helped demote Pluto, the man who had been leading the Planet 9 search for years, took a careful look. He recalculated the orbit based on the positional data from the two surveys, and what he found stopped him cold. The orbit had a tilt, a massive tilt, something like 120 degrees relative to the plane of the solar system. That is not a minor misalignment. That is a full-on, almost upside-down orbit. And here is the problem. Brown's entire model, the whole theoretical framework he had built over years of work, predicted that Planet 9 should have an orbit that is tilted, yes, but tilted by maybe 15 to 25 degrees. Not 120, not even close. If this candidate were real, it would be moving in a completely different direction than the one he had calculated. It would be orbiting backward, essentially, relative to the very gravitational effects it was supposed to explain. Brown explained it simply. An object in such an extreme orbit would not produce the kind of gravitational nudge that is herding the Kuiper Belt objects into their strange alignment. It could not. The math would not work. The entire edifice of evidence for Planet 9, the clustering of the distant objects, the tilt of the solar system's plane, the apparent gap in the Kuiper Belt, none of it could be explained by a planet orbiting at nearly right angles to everything else. So either this was a different kind of object, something we had never seen before, something that just happened to be there by coincidence, a wanderer, a rogue, a loner, or it was an artifact, a ghost in the machine, a coincidence of noise and old data, and as more teams looked at it, they began to suspect the latter. The two surveys did not agree perfectly. The motion was ambiguous. The object itself was so faint that it could have been a minor planet in the main asteroid belt that only looked far away because of a lucky alignment of viewing angles. It was a disappointment, a deep, sinking, quiet disappointment, but it was also a lesson. The theoretical debate, no matter how beautiful, no matter how mathematically airtight, had run its course. The equations could only take us so far. The computer models could simulate 1,000,000 possible orbits, but they could not tell us which one was real. The papers could argue until the ink ran dry, but they could not produce a single photon from a real planet. We had reached the false limit, the dead end of pure theory. There is a certain kind of frustration that comes with this. It is the frustration of knowing something is there, of feeling it in the numbers, of seeing its shadow in the movements of distant ice, and yet being unable to reach out and touch it. It is like hearing a voice in the next room, muffled, indistinct, but unmistakably human, and not being able to open the door. The door, in this case, is the limits of our technology. And those limits are real. They are not just about money or will. They are about physics. The light from a cold planet at 800 astronomical units is just incredibly, heartbreakingly faint, and it moves so slowly against the starry background that you have to compare images taken months, even years, apart to see any shift at all. The search space is just too vast. The signal is too small. The noise is too large, so the stalemate hardened. The search continued, but it was slow, halting, full of false starts and dead ends. Astronomers kept scanning, kept hoping, kept building better models. But deep down, everyone knew the truth. The theoretical phase of the hunt was over. The next phase, the real phase, would require a new generation of telescopes. Telescopes that could see the unseen. Telescopes that could stare into the darkness long enough and deep enough to catch the faintest glimmer of a world that had been hiding for 4.5 billion years. And that was the moment when the astronomers stopped arguing with each other and started arguing with the universe. They had done everything they could with the tools they had. Now they needed bigger tools. They needed a bigger bucket. They needed to build something that had never been built before. Because the hunt for Planet 9 was no longer a question of if, it was a question of when we would be able to see. The stalemate had hardened into a kind of weary resignation. The astronomers, the believers, and the skeptics alike were tired. Tired of the same arguments, tired of the false alarms, tired of the slow, grinding pace of the search. The theoretical case for Planet 9 remained strong, compelling even. The orbital statistics, the clustering of the extreme trans-Neptunian objects, the unexplained tilt of the solar system's spin axis, all of it whispered the same name, a massive planet, far away, hidden in the dark. But the whisper was not a shout, and the telescopes, as magnificent as they were, could not hear it clearly enough. The community began to shift its focus, not away from the hunt, but toward the tools. The conversation, which for years had been dominated by orbital mechanics and celestial dynamics, now turned to engineering. It turned to optics. It turned to the next generation of observatories that were finally coming online after decades of planning, of budget battles, of political manoeuvring, of sheer technical audacity. The Vera C. Rubin Observatory, perched on the Cerro Pachon mountain in Chile, was nearing its first light. Its secret weapon was not a single massive mirror, but a vast, almost impossibly wide field of view. A 3.2 gigapixel camera, the largest digital camera ever built for astronomy. Every 3 nights it would scan the entire visible sky. Not a sliver, not a patch, the entire sky, night after night, year after year. Its primary mission was to map the universe in motion, to find asteroids, comets, supernovae, anything that changed or moved. And that is exactly the kind of machine you need to find a ghost planet. You need a telescope that is not peering through a straw. You need a telescope that is looking everywhere at once. The Rubin Observatory was designed for this. Its data stream would be a flood, an avalanche. Every night, terabytes of images would pour in, capturing everything from the brightest stars to the faintest galaxies. The challenge, of course, was not taking the pictures. The challenge was finding the needle, the faint dot that moved just a little bit between one night and the next. The object that was too slow to be a main belt asteroid, too faint to be a known Kuiper Belt object, too distant to be a comet. The software would have to sift through billions of detections, comparing each one across multiple nights, looking for the telltale motion of something far away. And even then, even with the Rubin Observatory, the search would not be easy. Planet 9, if it existed at the pessimistic end of its predicted orbit, would be moving so slowly that it might only shift by a few pixels over an entire year. You would need to stack images, combine months of data, just to see it, and even then it might be so faint that it barely registers above the noise of the sky itself. The astronomers knew this. They knew the Rubin Observatory was their best hope, but they also knew it was not a guarantee. It was a chance, a powerful chance, a chance that came once in a generation, and so they waited. They watched the construction progress. They watched the camera being assembled, tested, shipped. They watched the dome being fitted with its massive shutter. They watched the mirrors being aligned, calibrated, polished to a perfection that defied human intuition. And they kept working on the theory, refining the search parameters, narrowing down the possible orbits, trying to predict exactly where the planet might be hiding, so that when the Rubin Observatory finally turned its gaze to the sky, they would know exactly where to look first. But there was a deeper, stranger possibility that began to surface, a possibility that, for some, was even more unsettling than the idea that Planet 9 did not exist. What if the reason we could not find it was not because it was too faint, but because it was something else entirely? Something that did not reflect light the way we expected. something that was not a planet at all, but a black hole. A primordial black hole, a hypothetical class of objects that some theorists believed could have formed in the chaotic, dense moments after the Big Bang. These black holes would be tiny, perhaps only the mass of a mountain compressed into a sphere smaller than an atom. But they could also be larger, much larger. A black hole with the mass of 5 to 10 Earths, a so-called intermediate mass black hole, would be only a few centimeters across. It would be completely invisible. It would emit no light, no heat, no radiation that our telescopes could detect. It would be a perfect shadow, a ghost in the machine of a completely different kind. The idea was strange, almost science fiction, but it was not impossible. Some researchers began to explore it seriously. If Planet 9 were actually a primordial black hole, it would explain why the search had been so fruitless. We were looking for a reflecting world, a sphere of rock and ice, when we should have been looking for a gravitational anomaly. The way to find a black hole of that size is not to see it, but to see its effect on the fabric of space-time. To look for tiny, fleeting magnifications of distant stars as the black hole drifted in front of them, bending their light with its intense gravity, a phenomenon called gravitational microlensing. It was a different kind of search, a search not for a point of light, but for a momentary brightening, a subtle wink in the sky. The surveys for microlensing already existed. They were designed to look for dark objects in the Milky Way's halo, for free-floating planets, for rogue worlds. Could they also find Planet 9? The hypothesis was intriguing, but it faced its own profound problems. If Planet 9 were a primordial black hole, its capture by the solar system would have been an incredibly rare event. The solar system had been orbiting the galaxy for 4.5 billion years, and in all that time it had only encountered one such object? It seemed unlikely, and even if it had been captured, its orbit would have been shaped by the gravity of the Sun and the other planets in a way that might not match the elegant predictions of the Planet 9 model. The theoretical machinery that had produced such a perfect fit for the Kuiper Belt clustering assumed a planet, an extended body with a certain radius and mass. A black hole would behave slightly differently. It would be a point mass, a singularity. The gravitational field would be the same from a distance, of course, but the formation history, the orbital evolution, all of that would be different. The black hole hypothesis added a layer of complexity that the data, already so sparse and ambiguous, could not easily resolve, and so the debate took another turn. Not just a planet or not a planet, but planet or primordial black hole. The believers began to divide into two camps, those who clung to the classic planet model and those who entertained the darker, more exotic possibility. The skeptics watched this division with a kind of weary amusement. They pointed out that invoking a primordial black hole was the last refuge of a desperate theorist. It was an explanation that could not be tested, could not be proven, could not be falsified until we actually saw the gravitational microlensing signal. And that signal might take years to appear. Decades. The black hole could be drifting through the outer solar system right now, completely invisible, and we would never know until it happened to pass in front of a background star, bending its light for a few hours, a few minutes, a fleeting moment of cosmic coincidence. The astronomers were running out of easy answers. They were running out of patience. The years stretched on. The Rubin Observatory was delayed, as every major observatory is delayed. The software was not ready. The camera needed more testing. The pandemic had disrupted supply chains, had sent engineers home, had slowed everything to a crawl. The same frustrations that plagued every large scientific project plagued this one. And yet, the astronomers waited. They had no choice. The universe does not care about our deadlines. It does not care about our funding cycles. It does not care about our desperate desire to know. It simply exists. It simply hides, and we, the tiny creatures on a tiny rock, must find the patience to wait for the light to arrive. And so we wait. But waiting, for once, is not a passive act. It is a technological siege. For years, the hunt for Planet 9 has been a game of shadows, of statistical whispers, of looking at the gravitational fingerprints left on a tiny handful of distant worlds. It has been frustrating, brilliant, and maddening, but that era is ending. The weapon we have been forging is finally online. It sits high in the Chilean Andes, on a mountain called Cerro Pachon, and its name is the Vera C. Rubin Observatory. Let me be clear about what this machine represents. It is not just another telescope. It is a paradigm shift. It is the difference between trying to find a single lost needle in 1,000 separate haystacks using a dim candle and flipping on the stadium lights over the entire field at once. The Rubin Observatory is a joint project between the United States National Science Foundation and the Department of Energy. It is named after Vera Rubin, the astronomer who stared at the rotation of galaxies and realized that something was very, very wrong. She saw that stars at the edges of galaxies were moving far too fast to be held together by visible matter alone. Her work provided the first concrete evidence for dark matter. It is deeply poetic, then, that an observatory bearing her name is now tasked with solving another cosmic mystery that has been hiding in plain sight. The heart of this beast is the Simonyi Survey Telescope. It boasts an 8.4-metre mirror. That is enormous, but size alone is not the trick. The real magic is the camera. They have built the largest digital camera ever constructed for astronomy. It is a 3,200 megapixel behemoth. Let me put that number into a human perspective. You would need 378 4,000 ultra-high definition television screens just to display a single full-resolution image from this camera. Each image it takes is large enough to capture the entire full moon. But with a resolution so fine, you could spot a golf ball from 15 miles away. But here is the thing. It does not just take one picture, it takes a picture of the entire visible southern sky every single night. For 10 years. The strategy is called the Legacy Survey of Space and Time, or LSST. It is exactly as ambitious as it sounds. Previous surveys, like the one that found Sedna, or the one that used the Hubble Space Telescope, were like staring through a straw. You picked a small, promising patch of sky, and you stared at it until your eyes bled. It worked for finding specific things, but it left vast, uncharted oceans of darkness. Rubin is different. It is going to map the entire southern sky, and a significant chunk of the northern sky continuously. It will create a movie of the heavens. And this is the key. It is an unbiased map. It does not care what it finds. It just sees everything. Now connect the dots to our missing planet. Planet 9, if it exists, is a terribly dim object. It is not reflecting much sunlight from 800 astronomical units away. But it is moving. It is orbiting the sun, just like everything else. It just takes 20,000 years to do it. The problem with a slow-moving object is that you need a baseline. You need to see it again and again and again over months and years to prove that it is not just a faint distant star or a galaxy. Rubin is built for exactly this. By imaging the same patch of sky every few nights, it will catch that one faint dot that has shifted a tiny fraction of a pixel between Tuesday and Thursday. It will see the motion. It will see the drift. Over the course of a year, that drift will become obvious, unmistakable. Dr. Mario Juric, an astronomer deeply involved with the project, has made a staggering estimate. He believes that Rubin will expand our known catalogue of Kuiper Belt objects from roughly 4,000 to somewhere around 40,000. That is a tenfold increase. Think about the implications. Right now, the evidence for Planet 9 is based on the strange, clustered orbits of about a dozen of the most extreme objects. It is a compelling pattern, but it is fragile. A skeptic can always argue that the sample size is too small, that we are just seeing the noise. But with 40,000 objects, the statistics become ironclad. The clustering either persists or it does not. The pattern either holds true across a massive population or it dissolves into random chance. This is what we call the direct test. If Planet 9 is real, and it is out there, and it is bright enough, Rubin will capture it. It will resolve a new dot of light in the extreme outer solar system, and then we will watch that dot move, and the mystery will be over. But there is another outcome, one that is just as scientifically valuable. If Planet 9 does not exist, If the clustering we see today is a statistical fluke, then as Rubin fills in the map with tens of thousands of new objects, that apparent grouping will fade away. The anomaly will vanish into the background noise of a properly understood solar system. Either way, we get an answer, and the timing is now. The Rubin Observatory began issuing its first official sky alerts in February of 2026. Those first images were not the deep, final survey data, but the machine was alive. It was seeing. It was cataloguing. The astronomical community has been holding its breath, knowing that the coming months represent the most direct, transparent test of the Planet 9 hypothesis we have ever had. The entire field has been looking at the calendar and saying, "This is it." But the universe, as always, had other plans. In the middle of 2026, while everyone was waiting for Rubin to start speaking, a different telescope threw a curveball. The Subaru telescope in Japan, a giant 8.2-meter instrument perched on the summit of Mauna Kea in Hawaii, was doing its own deep survey, and it found something. It found an object designated 2023 KQ-14. The astronomers gave it a nickname. They called it Ammonite. Ammonite is an extreme sednoid. Its orbit takes it far, far away from the Sun, deep into the region where Planet 9 is supposed to be pulling the strings. And the conventional theory would predict that its orbit should be tilted and aligned. It should be part of the cluster. It should dance to the same mysterious tune as the others. But it did not. Its orbit was different. It did not fit the pattern. Dr. Yukun Huang, who analysed the discovery, was blunt. He said, quite plainly, that the orbit of Ammonite weakens the case for Planet 9. This is the messy reality of science. You build a beautiful hypothesis. You make a prediction, and then nature hands you a piece of data that does not fit. Does it kill the hypothesis? No. A single outlier does not disprove the existence of a planet that could be 5 times the mass of Earth. But it complicates things. It forces the theorists back to the whiteboard. It raises the possibility that we have been misinterpreting the signal. It has also led to a far more radical alternative interpretation. What if Planet 9 was real, but it is no longer there? What if it was a real planet, a true giant, that formed in the early solar system and was later ejected by the gravitational chaos of the gas giants? This is not a new idea. Simulations have shown that the early solar system likely tossed out several massive bodies. They became rogue planets, drifting through the galaxy alone. The argument goes that the gravitational ghost of this ejected planet could still be influencing the orbits of the distant Kuiper Belt objects. In this scenario, Planet 9 was once real, but we are looking for a shadow. We are looking for an echo that has already left the room. And just to make things even more confusing, another candidate emerged almost simultaneously. Astronomers sifting through old infrared data from a previous mission spotted an unconfirmed object moving. And this one is a doozy. According to the preliminary reports, if this object is real, it might be more massive than Neptune itself. We are talking about a true super-Earth, a genuine giant lurking at the very edge of our solar system. The scientists are being extremely cautious. They know that infrared data is tricky. It could be an artifact, a glitch, a false positive, but it is there. It is a tantalizing, unresolved dot on the grainy archival plates. So, here we are. The summer of 2026 has become the most consequential season yet in the decade-long hunt for Planet 9. The Rubin Observatory is opening its digital eye. The Subaru telescope has thrown a wrench into the works with Ammonite. The old data has teased us with a possible monster. And we are caught in the middle, juggling 3 competing narratives. The planet that might be there. The planet that might have been there but is now gone. The planet that might be far bigger than we ever imagined. The answer, if it comes, may be just months away. That is the terrifying, exhilarating truth. We are standing at the precipice. We have built the machine. We have learned the lessons of a dozen failed hunts. We have the patience of Vera Rubin herself. And now, we simply let the light fall onto the mirror. We wait for the pixels to add up. We wait for the signal to rise out of the noise. It could be a single dot, moving against the static stars. Or it could be the slow, quiet realization that there is nothing there but emptiness, and that the solar system we grew up with is stranger and emptier than we ever dared to believe. Either way, the light is on its way, and we are finally ready to see it. Let us step back for a moment and appreciate the full arc of this search. The story of Planet 9 did not begin with the prediction. It began with a perplexing pattern noticed by astronomers who were studying the most distant objects in our own solar system. In the early 2000s, the discovery of Sedna, a small world with an impossibly distant orbit, raised eyebrows. Sedna never comes close enough to the Sun to be significantly affected by Neptune. Its orbit is a mystery. Why is it there? What put it there? Then, more objects with similar strange orbits were found. In 2014, astronomers Chad Trujillo and Scott Shepard published a paper noting that these distant objects had orbits that were all tilted in the same direction and clustered in space. The odds of that happening by chance were incredibly low. They suggested that a massive, unseen planet was herding them like a cosmic shepherd. 2 years later, in 2016, Konstantin Batygin and Mike Brown at Caltech published their landmark paper laying out the full theoretical case for Planet 9. They had run simulations showing that a planet 5 to 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than our own world, could explain the observed clustering. The hunt was officially on. Since that paper, the search has been relentless. Astronomers have used the Hubble Space Telescope, the Keck Observatory, the Subaru Telescope, and even the archival data from the WISE mission, which scanned the entire sky in infrared. They have looked for the heat signature of a planet that is still warm from its formation. They have looked for the reflected sunlight of a world orbiting in the dark. They have searched for its gravitational influence on the orbits of spacecraft like Cassini and New Horizons. And every single time, the answer has been the same. Not found, but not ruled out. The parameter space is vast. A planet at 800 astronomical units could be almost anywhere along its orbital path. It could be in the part of the sky that is hardest to observe, the galactic plane, where the stars are thick and the background noise is overwhelming. It could be fainter than we calculated. It could be covered in a dark, sooty surface that absorbs light instead of reflecting it. The possibilities are maddening. This is why Rubin is such a game changer. It is not just a better telescope. It is a different philosophy of observation. Previous efforts were like trying to find a lost dime in a dark parking lot by shining a single flashlight beam and methodically sweeping back and forth. If the dime was in the beam, you would see it. If it was not, you would miss it. And you could never be sure you had covered every inch. Rubin turns on the floodlights. It will image the entire sky, every few nights for a decade. There will be no more guesswork, no more hoping that the planet is in the tiny patch of sky we happen to look at. If Planet 9 is bright enough to be detected, Rubin will find it. Period. The question, of course, is, what is bright enough? That is the million-dollar variable. The brightness of a distant planet depends on its size, its distance, and its reflectivity, which astronomers call its albedo. If Planet 9 is a gas giant with a bright, icy atmosphere, it could be relatively easy to spot. If it is a rocky super-Earth with a dark, charred surface, it could be incredibly faint. The range of possibilities is huge. Brown and Batygin have estimated that the planet could have an apparent magnitude somewhere between 22 and 25. To put that in perspective, the faintest stars visible to the naked eye are around magnitude 6. A magnitude of 22 is about 16 million times fainter. It is incredibly dim. But Rubin can see it. The telescope is designed to reach magnitude 27 in its deepest exposures. That is 100 times fainter than the dimmest plausible Planet 9. So, if the planet is there, and it is within the survey area, Rubin will almost certainly see it. But here is the catch, the survey area. The Rubin Observatory is located in the southern hemisphere. It will have the best view of the southern sky. The galactic plane, where Planet 9 might be hiding, crosses both hemispheres, and the northern part of the galactic plane, which includes the constellation of Orion and the surrounding regions, will be harder for Rubin to see. It will not be invisible, but the coverage will be less frequent. This means that even with Rubin, there is a possibility that Planet 9 could be hiding in a part of the sky that is not covered as thoroughly. It is a small possibility, but it is not zero. The astronomers are aware of this, and they have plans to use other telescopes for targeted follow-up observations in the north. Beyond the direct detection, Rubin will also provide a flood of new data that will refine the theoretical models. Even if Planet 9 itself is never directly imaged, the pattern of orbits it leaves behind will become much clearer as we discover thousands of new Kuiper Belt objects. This is the statistical approach. If Planet 9 is real, the orbits of the most distant objects should show a clear signature. Their perihelia, the closest points to the Sun, should be clustered in one direction, and their orbits should all be tilted in the same plane. As Rubin adds more and more objects to the catalogue, this signal will either become stronger or disappear. If it strengthens, we will have indirect but powerful confirmation that a massive planet exists. If it weakens, we will have to accept that the original clustering was a statistical fluke, a random alignment that we read too much into. This is exactly how science progresses. We build a hypothesis, we make predictions, and then we test them against new data. The Rubin data will be the ultimate test. And then there is the rogue planet hypothesis. This idea is gaining traction in some circles, and it is worth exploring in more detail. The scenario goes like this. In the early solar system, there were more than 8 planets. The gas giants, Jupiter and Saturn, underwent a period of dynamical instability, migrating and scattering planetesimals throughout the solar system. In this chaotic environment, it is very likely that some fully formed planets were ejected. Simulations of the early solar system routinely show that 1 or 2 planets, with masses between Earth and Neptune, get tossed out into interstellar space. These are the rogue planets we now detect, drifting between the stars. The radical idea is that one of these ejected planets was massive enough to leave a lasting gravitational imprint on the outer Kuiper Belt before it was thrown out. That imprint, a kind of gravitational fossil, could persist for billions of years. The objects we see clustering today might be the remnants of that ancient interaction. They are still moving in the paths they were given 4 billion years ago, even though the planet that set those paths is long gone. This would explain why we see the clustering, why we cannot find the planet, and why Ammonite does not fit the pattern. It would mean that Planet 9 was real, but we are looking for a ghost. We are 1 billion years too late. The third candidate, the potential super-Earth found in the old infrared data, brings us back to the possibility of a real, present-day planet. This candidate, if it is real, is far larger than the original Planet 9 predictions. A planet more massive than Neptune would be a true giant, a world that would radically reshape our understanding of the solar system. Its discovery would be the biggest astronomical event of the century. But it also raises serious questions. How could such a massive planet have remained undetected for so long? Why have its gravitational effects not been seen in the orbits of the known planets? The fact that it was spotted in archival data and has not been confirmed suggests that the signal is weak and may be a false positive. The infrared data can be misleading because of confusion with background galaxies and dust. Still, it is a tantalizing thread, and it will be followed up with great urgency. As of late 2026, the situation is fluid. The Rubin data is pouring in. The initial sky alerts are being analysed. The first few months of the survey have already discovered thousands of new variable stars, asteroids, and supernovae. The pipeline is working. The software is handling the fire hose of data. And slowly the search for Planet 9 is moving from a theoretical exercise to an observational one. The astronomers are no longer just predicting where the planet might be. They are looking, and they are seeing. The next year will be decisive. If Planet 9 is out there, and if it is bright enough, we will see it. It could appear as a single faint dot in a Rubin image, moving slowly against the background stars over the course of weeks. The moment that happens, the world will know. The news will spread instantly. It will be a discovery that reshapes our place in the solar system, a reminder that our cosmic backyard still holds secrets. And if it does not appear, if the survey covers the entire southern sky and the northern sky is searched thoroughly, and nothing is found, then we will have to accept that Planet 9 does not exist. The clustering was a fluke. The solar system ends at Neptune, and we are alone in a vast empty expanse. That would be a profound discovery in its own right. It would mean that our models of the early solar system need to be revised. It would mean that the outer solar system is emptier than we thought, and that the processes that built the planets here were different from those that built planets around other stars. Either way, we win. We get an answer. The hunt for Planet 9 is a testament to human curiosity and persistence. It is a story of scientists who saw a pattern in the sky and refused to let it go. They built better telescopes. They wrote better software. They convinced funding agencies to spend hundreds of millions of dollars on a search with no guarantee of success. And now, in 2026, we are at the end of that road. The light from the distant world, if it exists, is already travelling towards us. It has been travelling for years, perhaps centuries, crossing the vast emptiness of the outer solar system. It will reach the mirror of the Rubin Observatory. It will be captured by the 3200 megapixel camera, and it will tell us once and for all whether we have a ninth planet or not. We are waiting, we are watching, and the answer is almost here. Somewhere past Neptune in the dark, something has been quietly bending the paths of distant icy worlds. The question that has haunted astronomers since the 1840s may finally be answered within the next few years. We are waiting, we are watching, and the answer is almost here. But before that answer arrives, before the Rubin Observatory turns its 3200 megapixel mirror toward the abyss, let us step back. Let us zoom out, far out, and ask ourselves a much bigger question. What does this entire hunt actually mean? Not just for the scientists hunched over their computers, not just for the planet hunters who have spent sleepless nights chasing a ghost, but for all of us, for our understanding of the cosmos, for the human story. This is where we put aside the orbital calculations and the gravitational anomalies for a moment, and we think about what we are really doing here. We are not just looking for a rock. We are not just trying to add one more number to a list of known planets. We are witnessing science in its purest, messiest, most electrifying form. The search for Planet 9 is not an isolated event. It is a textbook example of how discovery actually works, the way it has always worked, since the very first humans looked up and wondered. Think about it. The pattern is ancient. You have an anomaly, something that does not fit, a strange wobble, an unexplained orbit, a data point that refuses to behave. Then you have a hypothesis, a tentative guess to explain the oddity. Then comes the debate, the furious back and forth, the arguments in journals and conference halls and late-night email threads. And finally, if you are lucky, you get resolution, confirmation or refutation. This is the rhythm of science. It is not a neat line from ignorance to knowledge. It is a zigzag. It is 2 steps forward and 1 step back. It is arguments and egos and stubbornness and flashes of brilliance. And right now, with Planet 9, we are living in the thick of it. We are in the debate phase. The anomaly is real. The hypothesis is compelling. But the resolution has not come yet. And that is precisely what makes this moment so beautiful. Consider what the answer will mean, no matter which direction it takes. If Planet 9 is confirmed, if that telescope really does catch a faint dot of light moving slowly against the stars, then everything changes. Our solar system becomes larger than we ever imagined, more complex. A new class of planet, maybe a super-Earth or a mini-Neptune, hiding in our own backyard, patiently orbiting out there at hundreds of astronomical units. It would not just be a 9th planet. It would be a whole new category of world, one that we have no direct analogue for in our own neighbourhood. Planetary formation models, the ones that have been taught in textbooks for decades, would have to be rewritten from scratch. How does a planet that big form so far from the Sun? How does it survive out there, in the cold, without being ejected? The answers would reshape our understanding of how solar systems, not just ours, but every solar system in the galaxy, actually assemble themselves. It would force us to rethink the very definition of a planet again, and it would prove that the outer edge of our system, the place we thought was empty and boring, is actually a dynamic, living frontier. But what if Planet 9 is ruled out? What if the Rubin Observatory scans the entire sky, year after year, and finds nothing? What if the orbital clustering of those distant Kuiper Belt objects turns out to be nothing more than a statistical fluke, a cosmic coincidence that fooled us all? That would be a very different kind of lesson. It would be a cautionary tale, a reminder that human brains are pattern-seeking machines, and sometimes we see signals where there is only noise. It would be a sobering moment for the scientific community, a humbling reminder that limited data can lead to overinterpretation. But it would not be a failure. Far from it. It would be a triumph of the scientific method, because you do not need to find what you are looking for in order to make progress. Ruling out a hypothesis is just as valuable as confirming one. It would also mean that the Kuiper Belt, that ring of icy debris beyond Neptune, is even stranger than we currently believe. Something is causing those orbits to cluster. If it is not a planet, then what is it? A massive ring of debris? A primordial warp in the fabric of the early solar system? A gravitational echo from a passing star billions of years ago? Each of these alternatives would be its own profound discovery. The mystery would not disappear. It would just transform into a different mystery. And then there is a third possibility, one that many people do not talk about as much, Planet Y or Planet 10, or whatever we end up calling it. The possibility that the answer is neither a single giant planet nor a statistical illusion, but something in between. An object that is smaller than Planet 9 predictions, or further out, or in a completely unexpected orbit. Or maybe multiple objects, a whole new class of dwarf planets, or a ring of dark bodies, or something we have not even thought of yet. The point is, our solar system's planet count could rise to 9 or even 10. But each discovery would challenge our definitions. Would we call it a planet if it is half the size of Neptune? What if it is covered in ice and barely reflects any light? Would it still count? The International Astronomical Union would have to go back to the drawing board again, and every astronomer on Earth would have an opinion. That debate itself, the argument over what counts as a planet, is a sign of a healthy science. It means we are being forced to evolve our thinking, because nature does not care about our categories. Nature just is. We are the ones who have to catch up. Beyond the science, there is something else happening here. Something human. This search has captured the public imagination in a way that planetary science rarely does. You see it in the comment sections, in the online forums, in the late-night YouTube rabbit holes. People who could not care less about orbital mechanics are suddenly debating the eccentricity of Kuiper Belt objects. The conversation moves almost as fast as the science itself, and that is remarkable. It is rare for a scientific question, an open question with no answer yet, to grab hold of so many minds at once. Usually, the public only hears about discoveries after they are made. But with Planet 9 we are all waiting together. We are all in the uncertainty. And there is a special magic to that. It turns astronomy from a spectator sport into a shared vigil. Konstantin Batygin, one of the astronomers who first laid out the mathematical case for Planet 9, set the standard early on. He said, and it is still the rule today, until it is caught on camera, it does not count as real. That is the scientist talking. That is the humility and the rigour that makes this whole enterprise trustworthy. Because for all of our theories, for all of our beautiful mathematics and elegant orbital simulations, the universe has the final say. And the universe does not care how elegant our equations are. The universe will show us what it wants, when it wants. And we have to be ready to accept that, whether it matches our expectations or not. That brings us to the one certainty in all of this uncertainty. The outer solar system holds far more secrets than anyone expected a decade ago. Even if Planet 9 never materializes, even if we search the entire sky and find nothing, we have already learned something profound. The Kuiper Belt is not a quiet, static graveyard of icy leftovers. It is a dynamic, complex and deeply strange place. The orbits of these objects are telling us a story, and we are only just beginning to learn how to read it. Whatever the final answer is, we will come out of this with a better understanding of the region of space that lies beyond Neptune. And that is a victory, no matter how you measure it. So where does that leave us? Standing at the edge of the unknown, staring into the dark, the Rubin Observatory, when it finally turns its gaze skyward, will not just be looking for Planet 9. It will be mapping the entire visible universe in a way that has never been done before. And in that flood of data, among the billions of stars and galaxies and asteroids, there will be a signal, a faint, slow-moving dot, or maybe not. But either way, the answer is coming. The question that has haunted astronomers since the days of Percival Lowell, since the first hints of Pluto, since the discovery of Sedna, and the realization that something was wrong with the outer solar system, that question is about to be resolved. Maybe not tomorrow, maybe not next year, but within the next few years, the story will have an ending. And here is the thing about endings. They are also beginnings. Because every answer, no matter what it is, opens up a new set of questions. If we find Planet 9, we will want to know what it is made of, how it got there, whether it has moons, whether it has rings, whether there are more planets beyond it. If we do not find Planet 9, we will want to know what the hell is actually causing those clustered orbits, and that investigation will take us deeper into the Kuiper Belt, further out into the Oort cloud, to the very edge of the Sun's influence. The hunt will continue. It will never stop. Because that is what we do. That is what humans do. We look. We wonder. We push against the darkness until the darkness gives up its secrets. So, as we wait for the Rubin Observatory to send back its first images, as we count down the days until the mirror is fully operational, as we refresh the feeds and watch the forums for any hint of a discovery, let us remember something. The universe is not obligated to make sense to us. It is not required to match our theories or fit our expectations. But it is out there, waiting, and we are here, asking questions. That alone is extraordinary. That is the cosmic perspective. We are tiny, fragile creatures on a speck of dust in the vastness of space, and yet we are capable of contemplating the very edges of our solar system, capable of predicting the presence of a world we have never seen, capable of building a camera with 3200 megapixels and aiming it at the unknown. Whether that answer is a new world, a ring of debris, or a statistical ghost, one thing is certain: the hunt for what lies beyond is far from over. To understand why this hunt grips us so tightly, we have to reach back into the history of science itself, past the discovery of Neptune, past the cold nights of Lowell's Arizona Observatory, all the way to the very first moment a human being realized that the lights in the sky were not just lights. They were worlds. The moment the nomadic herders of the ancient Near East noticed that 5 of those wandering stars behaved differently than the rest, that they moved in loops and retrograde arcs, that was the beginning of planetary science. Those 5 objects, visible to the naked eye, were our entire cosmos for millennia. Mercury, Venus, Mars, Jupiter, Saturn. That was it. The universe was small, orderly, comprehensible. Then came the telescope. Galileo pointed his primitive tube at the sky in 1610, and suddenly the cosmos exploded. He saw moons orbiting Jupiter. He saw that Venus had phases. He saw that the Milky Way was not a cloud but a river of stars. And in that moment the universe became infinite. The discovery of Uranus in 1781 by William Herschel, a musician turned astronomer, was the first time a planet had been found that no human eye had ever seen before. It was a shock. The solar system was larger than anyone had dreamed. Then came the discovery of Neptune in 1846, a triumph of mathematics, a planet predicted before it was seen, a validation of Newtonian gravity so profound that it seemed the universe had been entirely figured out. There could be no more planets. The gaps were filled. But the universe does not care about our satisfaction. The discovery of Pluto in 1930 was a strange echo of that earlier triumph. It was found by a young farm boy named Clyde Tombaugh, who had spent months comparing photographic plates, flipping back and forth between images, looking for a faint dot that moved, and he found it. But from the very beginning, Pluto was wrong. It was too small, its orbit was too eccentric, it was a misfit. And for decades, astronomers convinced themselves that Pluto must be just the brightest member of a vast swarm of icy bodies. They were right. The Kuiper Belt, finally confirmed in 1992, showed us that the outer solar system was not empty at all. It was crowded, and it was in that crowd that the first hints of a larger body began to emerge. Now we stand at a similar crossroads, but the times have changed. The mathematics that predicted Neptune was simple Newtonian gravity. The mathematics that predicts Planet 9 is chaos. It is orbital mechanics on timescales of hundreds of millions of years. It is the subtle dance of gravitational perturbations, a whisper in the data that only emerges after thousands of observations and hundreds of thousands of computer simulations. The astronomers who make the case for Planet 9, Batygin and Brown, are not looking at a wobble in Uranus's orbit. They are looking at a clustering of 6 objects in the distant Kuiper Belt, all with orbital angles that tilt in the same direction. A signal so improbable that it screams for an explanation. They have calculated the odds. The probability that this alignment is random is somewhere around 1 in 10,000. That is not proof, but it is a powerful clue. The detractors, and there are many, point out that our sample size is tiny. We know about only a few dozen objects in that region of space. Our telescopes are biased. We are more likely to see objects at certain distances and certain inclinations. The clustering could be an artifact of observation, not a real feature of the sky. It is a valid criticism. It is the kind of skeptical pushback that makes science self-correcting. And it is why the Rubin Observatory is so crucial. When the Vera C. Rubin Observatory begins its legacy survey of space and time, it will image the entire southern sky every few nights for 10 years. It will see everything that moves: asteroids, comets, Kuiper Belt objects, and if it exists, Planet 9. There will be no bias. There will be no small sample size. There will be a complete census of the outer solar system. And that is where we are now. Waiting. The mirror is polished. The camera is assembled. The software is being tested. The observatory sits on Cerro Pachon in Chile, a mountain that reaches into the thin, clear air of the Atacama Desert, one of the driest places on Earth. It is the perfect location. The sky is dark, the atmosphere is steady, the survey will begin soon. And when it does, the data will flow at an unprecedented rate. Every night, the telescope will generate 20 terabytes of images. That is 20,000 gigabytes. Every single night, for 10 years. No human can look at that much data. The discovery of Planet 9, if it comes, will almost certainly come from a computer algorithm. A piece of software trained to spot the faintest moving dot among billions of static star-stars. The algorithm will flag it. A human will check it, and then the news will spread. But the search for Planet 9 is not just about the data. It is about the limits of human knowledge. Every time we push the boundary of our detection technology, we find something new. When Galileo turned his telescope to the sky, he saw things no human had ever seen. When Herschel built his giant reflector, he found a planet. When the Palomar Observatory scanned the sky in the mid-20th century, it found quasars and pulsars and the first hints of dark matter. Each new instrument opens a new window. The Rubin Observatory is that window for our generation. It will see the faint, the slow, the hidden. It will see the objects that have been orbiting in the dark for 4.5 billion years, untouched by sunlight, unobserved by human eyes. And among those objects, there will be surprises. The most profound lesson of the search for Planet 9 is not about planets at all. It is about the nature of certainty. We live in a time where information is abundant, where we can look up any answer within seconds. But the universe does not give up its secrets easily. The outer solar system has held its mystery for centuries. It will hold it for a few more years, and then at some point the answer will arrive. It may come as a faint dot in a series of images. It may come as a gravitational signal in the orbits of distant comets. It may come as a whisper from the deep past, a remnant of a star that passed close to our sun billions of years ago, scattering debris across the sky. The answer will come in the language of the universe, which is mathematics and motion and light. and we will have to be ready to understand it. So as we wait, we can take comfort in the fact that this is not a passive wait. We are not just sitting here, refreshing a web page. We are part of a grand tradition. Every person who reads about Planet 9, who discusses it with friends, who wonders about that dark space beyond Neptune, is participating in the great human project of understanding the cosmos. The scientists are the scouts, but the journey belongs to all of us. When the discovery is announced, it will not be a private moment for a few astronomers. It will be a shared moment for humanity, a new world revealed, a new chapter begun. The pattern of history tells us that the solar system is far stranger and far richer than any model we can construct in our minds. Every time we think we have it figured out, the universe throws a curveball. Uranus was supposed to be the last planet, then Neptune, then Pluto, then the Kuiper Belt. Each time our model grew. Each time we had to expand our definition of what a solar system could be. Planet 9, if it exists, will be the next expansion, and if it does not exist, the expansion will come in a different form. Perhaps we will discover that the clustering of Kuiper Belt objects is caused by a massive ring of debris, a remnant of the early solar system that never coalesced into a planet. Perhaps we will find that the clustering is a gravitational echo from a passing star, a visitor that came and went billions of years ago, leaving its signature frozen in the orbits of distant worlds. Each possibility is a door. Each door leads to a deeper understanding. We are at the threshold. The door is about to open. The answer is out there, moving in the darkness, following its ancient orbit around a star that it barely sees. And we, on our little planet, are straining our eyes, building our machines, waiting for that faint flash of light that will answer the question that has haunted us for generations. Whether it is a planet or a ghost, one thing is certain. The hunt has already changed us. It has made us look further. It has made us think bigger. It has reminded us that the universe is still full of secrets, and that is the greatest gift of all. So here we are. We have travelled a long way together, haven't we? From a wobble in the orbit of a distant blue world in the 19th century, to the relentless search for a hidden giant that has consumed astronomers for the better part of a decade. We started with the mystery of Uranus, that unruly planet that just wouldn't follow the rules. We watched as the hunt for the culprit led us to Neptune, and then, years later, to the tiny, icy disappointment of Pluto. For a long time, that was it. We thought we had found the end of the solar system, but the universe is never that tidy. The clues kept piling up. The strange, synchronized orbits of the most distant objects we have ever spotted. The computer simulations that said, over and over, there is something out there pulling the strings. It is a story of dead ends and stubborn hope, of data that whispers while theories shout. And now, it is a story that is hanging in the balance. We are standing right at the precipice. The evidence is compelling, maybe more compelling than it has ever been for any undiscovered planet. But compelling is not the same as proven. The skeptics have their arguments, and they are good ones. The mathematical models could be flawed. The observed clustering of orbits might just be a trick of the light, a bias in our own limited surveys. We have been burned before. We know how this story can end in heartbreak, but this time it feels different. Because the tools are finally here, the Vera C. Rubin Observatory is no longer a dream on a drawing board. It is a machine of light and glass, sitting high in the Chilean mountains, ready to turn on its giant camera and take a picture of the entire southern sky every single night for a decade. It is the cosmic net we have been waiting for. If Planet 9 is out there, lurking in the dark, Rubin will find it. It might take a month, it might take a year, but the verdict is finally within reach. We are not just wondering anymore. We are about to know, and that is where you come in. This channel, This is Space, is not just a place for facts and figures. It is a front row seat to moments like this. We are not here to give you the answers after everyone else has them. We are here for the journey. The late nights of speculation, the moments when a new paper drops and changes everything, the nail-biting wait for the next batch of data. This hunt for Planet 9 is one of the greatest detective stories in the history of science, and it is happening right now. You are not just watching a video, you are part of the audience that will be here to celebrate the discovery, or to grapple with the mystery when the answer comes. So do not let that moment pass you by. Hit that subscribe button, ring the bell. Make sure you are here when the story finally breaks, because when it does, the world will be watching, and I want you to be watching right here with us. This is a story that is still unfolding, and you are here for it. There is a real sense of community in this together. We are not just passive observers. We are explorers sitting at our screens, connecting the dots, asking the same questions that the scientists are asking. Every time you watch, every time you share a video, every time you leave a comment with your own theory, you are adding to the conversation. You are helping to keep the wonder alive. And trust me, there is so much more wonder coming your way, because once we solve the mystery of Planet 9, the solar system does not get any less strange. We have barely scratched the surface. We are going to take a deep dive into the Oort cloud, that immense frozen shell of comets that wraps around our solar system like a bubble, a place so far out that it is practically interstellar. We are going to look at the weird visitors from other star systems, like Oumuamua and Borisov, and ask what they can teach us about the galaxy. And we are going to look out even further, beyond our own neighbourhood, into the wild, wonderful chaos of exoplanets, where we are finding worlds that make science fiction look tame. There is a universe of stories out there, and we are only just getting started. So, here is the bottom line. The universe is under no obligation to be simple. It does not care about our categories. It does not care about what we want to find. It will reveal its secrets when it is ready, and often it will reveal them in ways we never expected. Planet 9 might be a massive dark world waiting in the shadows, or it might be a ghost, a beautiful mathematical illusion that teaches us something even deeper about gravity and the structure of space. Either way, the answer is coming, and when it does, we will be here. We will see you there, under the stars, with the data in hand and the questions flowing. The universe is under no obligation to be simple, but it is always, always worth exploring. We will see you out there.